All right, maybe give it another minute just to see if anyone else comes in. Things seem pretty stable. Should we start? All right, welcome everyone. Thanks for coming to my talk. Thank you BSDCan organizers and University of Ottawa for hosting me. So today we're going to talk about model checking. I've put together some examples of using this in the BSD userland and also a very simple kernel module. So we can kind of talk about that. So to kind of start with here, let's talk about why we care about model checking, especially now. The threat landscape right now is changing. We see this already with large language models. All these drive-bys we're getting currently with CVEs. Some of them are good, some of them not so good. A lot of vulnerability reports come in. It's getting overwhelming. We can look at other open source organizers as well that are just being completely buried in automated vulnerability reports. Each one of these things have to be looked at. And the other thing is we have to figure out if we've actually fixed the issue when we patch it. And so, this is becoming a significant issue. So if we just triage these issues, we're kind of just treading water unless we can get in front of it. To do that, we have to find a way of raising the bar. I think that the BSD is just the way that the code is organized, and FreeBSD, NetBSD, OpenBSD actually makes it an excellent candidate for doing something like this. So the question is, what can we do here? So I've been developing system software, firmware, and languages for 27 years. For the past 10 years, I've been studying a subset of programming language theory and formal methods, really with a focus on finding any sort of practical solution to this. Formal methods is a big area. A lot of it's theoretical, a lot of it's academic. My focus has really been, what can we do? What can we actually accomplish in a realistic scenario? I also had an opportunity recently to spend some time at Google on their kernel team doing some triage for their fork of the Linux kernel. You would see all these CVEs come in, and we'd have to figure out, how it affects their patches, how it affects whether these are things we need to patch right away, we need to live patch it, we can wait. It's a lot. Now I was there when Linux kind of went from having separate MITRE-based CVEs to becoming their own CNA, where suddenly everything was a CVE. You see a small error, you fix that, well, make a CVE for it. And so it kind of went from seeing maybe a dozen or so CVEs once we filter things out, seeing hundreds a week, and it started becoming a bit overwhelming. And since then, with large language models, I'm sure it's only gotten worse. So let's talk about formal methods for a moment. It's a set of rigorous mathematical techniques for the specification, development, and verification of software and hardware. We're kind of trying to shift the goalpost here from just testing, with empirical tests, which are great, to trying to verify the absence of certain errors and certain classes of errors. We do this by building up specification. We try to build up the properties that we expect software to have, be it function contracts. This is what a function is expecting as input. This is what a function is going to provide for side effects and output, to data structure and other types of recursion type invariants. This is what we expect to happen within the body of a loop, so on and so forth. And there are approaches for this ranging from calculus of constructions to model checking. Good example of a calculus of constructions, or even inductive dependent typing would be something like SEL4, which has a major proof for it. It's an entertaining read if you get a chance to read the papers on SEL4. So let's talk about satisfiability. Satisfiability kind of takes us into more of a subset of formal methods, which is can the solution be found for a large Boolean formula? If we build up a large, say, propositional calculus of a large formula, all these things have to be true for this to be true. Can we solve this? It turns out, in 1962, DPLL actually came up with a decent algorithm for a generalized solver for this, and it was proven to be NP complete. But there have been additional optimizations such as conflict-driven clause learning and all the other things that really kind of sped this up so it becomes usable. So basically how this works is we specify Boolean formulas in conjunctive normal form format, and then reduce them via backtracking with EPLL or conflict-driven learning with CDCL. So SMT, or satisfiability modular theories, it kind of builds on top of this. And this, it can be as simple as trying to simulate like integer operations as like a Boolean circuit to, actually building some sort of exits into the process and doing some additional logic on this. And SMT really takes us to a level where we can use this for doing things like model checking. And so with model checking, and in particular for our cases, bounded model checking, we're checking whether a finite state model of a given system matches a specification. So we can transform this into that same CNF form that we saw before, and really all the more we're doing is just saying, okay, we have all these properties that we put together. We're going to negate these and then look for a solution that violates one of these properties. And so if the SAT solver finds a solution, it's a counterexample demonstrating a case where the specification fails. And this is actually very useful. So CBMC, the C-bounded model checker, which Kronig and his team put together starting in 2004, it extends this model checking concept to C. So you can directly model check C, which is great. And this is a tool I'll actually demonstrate in this talk. There's a front end called GoToCC that kind of works like Clang. It takes all the same arguments. There's a GoToGCC that works just like GCC. And there's even, if you're a Microsoft person, there's even like a Microsoft front end as well. And so you can kind of just plug this into your same build flow, and the output will be one of these programs. There's a lot of instrumentation options that we can invoke, either at once or all together, to find counterexamples, things for like memory safety, integer overflow, checking for memory leaks, checking for user assertions. It's actually really impressive, the sorts of things you can do. You can even use CBMC to automatically derive unit tests, which is neat. So the instrumentation, as I said, we can skip that, I already said that. So the first example I have here is a kernel module I call modFido. So Fido, or filter-do, it's a do-as clone that I built using a model checking. You can kind of, I don't know if you guys are familiar with looking at the source code of do-as, but it's like a freaking haiku. It's so beautifully done and put together. You read it, it's like I think it's around 100 lines of code, and it just does everything that you would expect. And so, I'm much more of a prose guy, so when you look at the actual source code for Fido, it'll look more like, ugh, but it works. And one of the issues that I saw using do-as, the portable do-as for FreeBSD, is it doesn't have the same sort of Veroth credential caching that you have on OpenBSD. On OpenBSD, the credentials are actually associated with the TTY, and it's deeply integrated into the kernel itself, which is nice. So you log in, you authenticate using BSD auth, or in this case, a FreeBSD PAM, and then you can actually cache the real user ID and an expiry time. And the next time you go to perform a do-as command, it just verifies this by looking directly at the TTY, making sure that the user that owns the TTY and the actual cache credential and the current user actually matches, and then it checks the expiry time. And so this, kind of works similarly to like how sudo or something else works, but it's all kind of integrated into the kernel. I thought that was interesting. I wanted to have an opportunity to, kind of play with that and see, well, could I do that on FreeBSD? So I do bad things in this module because I really just wanted to demonstrate how things are done, how we can model check this. So I am hooking like sysint and actually like, building like a custom ioctl filter, doing some hooking of, pseudo terminals so I can see when they close. But, we can do better, but this is more of a didactic example. So, please don't at me. So before we get into actually looking at the demo itself, let's talk about some practical considerations of model checking. The first is the issue of state space explosion. So model checking scenarios have to be kept small, and loop unwinding has to be kept to a minimum necessary. Otherwise, it's a combinatorial explosion. Very quickly it can get out of control, and you won't actually be able to verify it. And so there are techniques you can use to kind of do this. The biggest technique is, try to model check function by function. Try to, and we'll get into more things here in a sec. And remember that really, we should be looking at model checking, especially if we're looking at it from a practical perspective, to complement what we can already do with testing. Testing, we can verify how software works, whether it's meeting certain features and that sort of thing. Model checking is more about, or at least how I like to use it, it's more about looking at the safety and in crucial areas, the correctness. So, so if I'm parsing like, data coming in from an untrusted source, I want to make sure that parse is correct. I can do that with CBMC. I can also do that with testing, of course, but CBMC at least gives me the ability to start ruling things out. I can rule out there's never going to be a chance of a buffer overflow or an integer overflow with what I'm doing. So this leads us to the concept of compositional verification, and this is where we start speeding up model checking. And really what we can do is if we use Hoare logic, preconditions, postconditions, and variants, we can start constraining how a function should operate based on a function contract. So the function contract, we say we expect that inputs are going to look a certain way, and this is the expectation of the function. We can verify that outputs and side effects are going to look a certain way, and that's kind of like the postconditions of the function. And then with invariants, we can check things like if we modify a data structure or we use like a kernel log or something like that, that we're properly releasing it when we need to, and that sort of thing. If we do this, then what we can actually do is we can substitute the function that we're model checking with a shadow function when we model check other functions. And so this shadow function, it ends up working the same, it fulfills the same contracts as the original function. So it passes the same precondition checks, passes the same postcondition checks, but instead of performing the actual work of the function, it's really more complex and requires a lot of frames, we can just do a little bit of non-deterministic behavior. And that models all possible outputs, for any possible input. And so it's a little looser, but in the case of verifying the safety of a function, that's fine. We want to verify every output that we may get from a function and make sure that our function that we're instrumenting is correct with respect to that. And so if we verify that the shadow function is performing the same preconditions and postconditions, that gives us good soundness so we can say, yes, we can use this for safety verification. All right, so let's actually take a look at this. And of course, the famous quote from Don Knuth here, beware of bugs in the above code. I've only proved it correct, not tried it. So if you look at this function, DIOC set veroth, the handler for this, the way that doas works is you end up having 3 ioctals that it operates against, or that it uses in the TTY. Set veroth basically sets the credentials. So, for this real user ID, set an expiry time, and then that's cached. And then check veroth will actually check that against the real user ID, querying it, and to make sure that the cache time hasn't expired yet. And then clear veroth just clears these credentials. So this function here, this is the handler that we have for set veroth, and we can look at the function contract preconditions. So in this here, we're expecting that the instance of the FIDO data that we were putting for this module is correct. So we define like a global type that kind of holds our red-black tree that we use for caching credentials, and so on and so forth. And this property just verifies it. The thing being passed in is correct. We verify also that currently the kernel lock that we've associated with this instance is not locked. We can verify here that the thread is valid coming in. And finally, the ioctal arguments that we're passing into this handler are within the range of what we expect. Post conditions, we're expecting that this function returns one of the error codes that we expect for this ioctal system call. We're fulfilling our contract with the ioctal. And secondly, that coming out, the kernel lock is unlocked. So if we lock the kernel lock when we do things in there, every execution path has to unlock it. So if you look at the implementation here, we can see at the beginning, we define a macro here that actually checks these preconditions. So that just runs everything in these preconditions here that we see. So the macro kind of expands out as just being an inline function. It ends up getting called. And that does all this verification at CBMC runtime. Here we get the TTY pointer. This is just a helper function that tries to find the right TTY for this operation, which gets a little interesting. We do a simple privilege check. We get the current uptime, and we extract this to a timeout duration. We set some bounds on it, and then we basically pre-compute and try to figure out what this entry should be. If there's an entry that already exists, we'll just update that entry and then unlock and free. Otherwise, we'll insert it. Now, the question is, what happens, if we have like this edge case here and we forget to unlock the mutex? Well, actually kick this off and run it. Whoop. We'll see that the command failed. And sorry, it's a little, there we go. And we can actually see that this property was violated. So it's kind of interesting. And as another, for instance, what happens if we don't do a bounds check on this timeout duration? So in this case here, the timeout duration is being copied in from the user process. If the user gave like a negative value or gave some other strange value we're not expecting, and we don't actually check that, oh, wait. Okay, well, apparently I don't check that. Forget I said that. That's missing. Let's do the boundary check on current seconds. And that's something else to kind of put in mind here too, as well, is that the model checking is only as good as your specification. If you don't actually verify something in the specification, it can cause an error. So here we go, this one failed. And we can see the reason why it failed is because we have arithmetic overflow on assigned value when we do this addition. Okay, what about forgetting to free this value? So in this case here, if we find a value already, we just update the value and then we free the original value outside of the lock. If we forget to free this, that's going to cause a memory leak in the kernel, which is not a good thing. So we kick this off here, and we'll actually get an error coming back saying that the memory was never freed. And this trace, if you go through the trace, you can actually reconcile this to find out where that memory was that wasn't freed. It's a bit of a pain sometimes, but at least it's a start. There are plenty of other techniques you can use to try to narrow this down. You don't necessarily have to use a trace to do it, but the good thing is that the trace tells you that, hey, this failed. You're leaking memory. And that's useful. And yeah, if you've got debug mode and everything else set up and you unload a kernel module, it'll let you know as long as you properly tag your allocations that, hey, you're leaking memory. But by then, it's kind of difficult to find out where or why. And so this really helps to narrow this down. So any questions so far? Okay. Well, moving on here. I can go into many more examples of things that you can do in ModFido. I think that the main takeaway from this is we can set up function preconditions, function postconditions, and we can run verification. Oh, there is one more thing I guess I could show. So this is kind of an example of all the files that we pull into for verification. So we can see we have a lot of shadow methods that we define up toward the top. And so any functions that call into this original function, we shadow. And that kind of makes things a little easier. And you can see, for instance, we shadow some of the kernel functions like copy in, get SB in uptime. mutex destroy, mutex lock, so on and so forth. CPMC actually does have concurrency support, so you can model some concurrency stuff. I don't do it here, but it could easily be done just by spawning separate threads and seeing what happens when they interact. It's a little, it doesn't run quite as fast as this does, but it does run in reasonable time. Let's see here. So let's take a look at something that actually calls this as an example. Oop. There we go. So here we can see the shadow implementation of that same set veroth handler. As you can see, it's much easier because all the more we're doing here, we're checking preconditions, checking post conditions, and then we're just assuming that the return value that we generate matches this error code that we expect for the ioctl syscall. And so that's really it. This property will look to see if it succeeded or it failed, and regardless of what happens there, it'll propagate out. So this significantly simplifies this when we're calling this function from another function. So for instance, let's take a look at, here's the hook that I have for hooking the ioctl itself. So this gets called every time an ioctl syscall is called. And as before, we checked preconditions. And here you can see our custom set veroth ioctl that we've defined, and we actually call into this. And so when we're model checking this, we're free to substitute the shadow version of this handler for the original one, which simplifies this model check and makes it run faster. And so that is kind of the way that we keep these model checks going fairly fast. If I were to kick this off, the entire model checking for this, in fact, I can go ahead and do that. The entire model checking for this module here, oops, let me do this. Just kick it off here. Give it a second to build. Here it's running all the model checks for this module. And we can see it took 15.62 seconds in real time, which is fairly decent. There is kind of a lot of belief that model checking has to be slow. If you go through this process of compositional verification, you can do it fairly quickly, which is nice. And this is running in a cloud instance, so it's not like this is the fastest machine out there. All right, so moving back here. Oh, there we go. So Fido itself is just a clone of Duaz in the userland side. So it's a setuid binary that it parses an optional config file to filter out policy decisions. So we can kind of set up any sort of policy decisions we might want, like allow members of wheel to perform the Fido operation and run commands as root. Filter and only allow them to run these commands, like only allow them to run like shutdown or restart or something, or maybe allow them to do audio I/O if they belong to the audio group. Exclude maybe this other user from this, even though wheel's allowed, wheel except for this person, because we can't really trust this person to do things right. However that policy decision may be, you can use the config file for doing that. By default, it just assumes that anyone who belongs to wheel is allowed to perform Fido. Next thing this does is, since this is running setuid root, and since we want to have the ability of checking a config before copying it over, it actually does a fork and exec to do the parse on the config file descriptor. And so it'll open the file descriptor, it'll do whatever fstat it needs to do, and then it'll do a fork and exec and immediately drop into capsicum, cap enter. Or on the OpenBSD side, it'll do a pledge and unveil, and only pledge the standard I/O. And so that way we kind of limit what could be done if something were to go wrong with this is basic defense in depth. We can model check things, but our model checks could be wrong, and so we definitely want to make sure we still keep up with runtime mitigation, just like what we would with anything else. So it goes through, does this. At the end of it, the result of the policy decision is returned, and if it's approved, FIDO will run the command under the returned user and group. Basic stuff. So we can take a look at this as well. Let's see here. Trying to find a good example. Let's look at one of the scan methods here. So let's okay, yeah, one of these is just as good as any other. So this scan keyword permit here. If I can find the right, oh, that's right. We actually want the complete version of this. One moment. You're looking at permit, right? 14. This is just a simple, in the scanner we wrote, I did a very simple scanner and then our parser for actually parsing a config. And so this actually runs the scan on a permit. And so if we take a look at the complete token keyword, there we go. We see we got function contract preconditions and postconditions as before. One of the things we want to do here is we want to verify that the details structure that we're passing in, this holds all of the token details that we're collecting when we do the scan, that this has it points to a region of memory that's the right size. We're not doing some sort of a buffer overrun or something else. And the other thing, of course, we'll verify that the scanner that we're using for this is valid. On the post conditions, we're expecting it to, if it doesn't respond with bad input or EOF, then we're expecting it to be either permit or username if it's not permit. You can imagine you could have a user that starts with permit, and then we verify that the indices and everything else are within the range of what we expect. Now, if we look at this function here, we'll see that toward the end here, we actually save these details. And if we look at this function, we can see that we're just caching along indices, and then we're using these later on to actually pull out a string and examine it, for certain other operations, like say an identifier. So the question is really, what happens if we compute this wrong? So in this case here, this would cause a buffer overrun for sure. So if we kick this off, it's a little bit slower, but give it a sec. Give it a sec. There we go. So when we go to parse this, we can actually see that we violated the property that we're checking for about the length of the index. And so this ensures that even if we have like a weird edge case or something where we make an assumption about the way that offset should work, that we can verify this. And so that's actually very useful. So we kick this off again, and it should pass. And so that kind of demonstrates, a nutshell, the sort of stuff we can do with function contracts and verification. And as you can see, this all kicks off, runs fairly fast. On this side, again, we're in a cloud instance, so it's a little slower, than what you would expect, say, if you were running on a laptop or a desktop that's about 2 years old or newer. It will be a little faster, but performance-wise, it's not terrible. And the nice thing about this is, when you're doing model checks, you don't need to actually do this in the source tree as everything else. You can, but you could totally move this into a separate source tree that looks into that. So say if you were model checking kernel modules or the kernel itself, you can actually define all the preconditions and the postconditions in a separate header that you use just for model check time. And so this kind of allows you to do this effort in parallel while keeping this clean on the kernel side. So you don't have to add all these artifacts into the kernel source code itself, which is really nice. All right, so let's go back to slides. Any questions so far? Yeah?
Is there a runtime overhead?
Okay, I'll repeat that. Is there a runtime overhead? No. So the nice thing about this is all the model checking runs just at compile time and analysis time. All the macros that I have in there for the precondition checks, those are compiled out at compile time. So there's no runtime overhead, which makes this actually really nice. Yeah?
How long between the time you spend writing the figure code or the shadow function? How many time you spend to write all this?
I find, I'll repeat the question. How much time do I spend on doing this?
Yeah, shadow part.
And shadowing? Yeah, so I find that it takes about the same amount of time as it takes to unit test code. So it's actually fairly fast. It doesn't require a lot of significant additional work. If you go through the process of setting up your contracts and setting up all your properties that you have, then from there, actually building out the model checking scenarios, building out the shadows and everything else, is just writing code that passes the contracts that you've already defined. So it actually goes fairly fast. Like anything else, it's a learning curve. So the first few times you do it, it'll take a little longer because you haven't done it before. Once you get used to it, you can whip these out real fast. Most of the work that I did on Mod Fido, I did in I did the Mod Fido itself in a couple hours, and then most of the work for the actual model checking itself, it was done in half a weekend. It didn't take that long. Yeah.
That URL is 404. Private?
Yes, I will open up these URLs afterward. The projects are currently private. I was planning on opening them as soon as the talk's over. So they will become available as soon as we're done here, and I'll just go in and mark them. I guess what I should probably do, at the very least, is I should actually demo this, right? I mean, if I wrote this, we should at least see that it works, right? So if I do a KLD load on this guy here, unfortunately I do have to use sudo to do this. This loads a module. Now, if we log in and say I want to do just ls, Fido ls. Now this much I don't need the module to do because it's just prompting me for a password. But if I want to run ls again without typing in a password, it needs the module. So there we go. That shows we have the cache credential. It's actually tied to the TTY. Once we log out and log back in, it'll prompt me again. As you would expect. Also, if we wanted to wait for 5 minutes, we'd see that it does expire as you expect. So it does work. All right. So any other questions before we move on? Yes?
Yeah, I just had one question. So I'm glad that you kind of demonstrated this maybe inadvertently, but like a problem that I've observed with formal proofs of code sometimes is, okay, we proved it, but we proved the wrong thing. And now there's other invariants that we possibly missed. So I'm curious what your methodology is when you decide what invariants you want to verify, how those accurately represent what it is you're trying to prove in your threat model, and so on.
Okay, to repeat the question, you're asking, noting that, yes, we absolutely can miss things when we set up properties for formal verification. And really, what is my methodology for ensuring that I can find these and verify what's missing or not? Is that a fair question? Okay, so the answer is, just like anything else, there's no such thing as perfection. And also perfection is kind of the enemy of good enough. When we go through this process, we're going to make mistakes, but over time we will find those mistakes and we can go in and fix them. What's nice about formal specifications is when we do find that we've made an error between specification and the actual implementation, we're free to go in and update the specification, make it better, right? The other thing is, we're going to verify these things for safety. We're going to unit test them for actual functional capability. The two are complementary. So I don't recommend using just formal methods or model checking. I recommend using that in conjunction with unit testing. And I think that the two together complement each other very well. The other thing to consider with this as well is that, you're going to still have CVEs that come down, right? You're still going to have vulnerabilities or other errors that are reported by users. When these happen, that's time to actually go back and take a look at the specifications and ask yourself, why did I miss this? And at that point, most likely what you're going to discover is you may have an edge case, or you may have actually discovered like an entire class of error that your specification is missing. Once you find that, once you identify it, you update the specification by updating the properties across the board, and now that entire class has been eliminated. Does that answer your question?
Yeah, thank you so much.
Any other questions?
I'll ask one more.
Okay, sure.
Yeah, so you picked CBMC. I'm curious why. So like, I'm not sure if you've seen like pharmacy from.
Yes.
Yeah, so like, I guess maybe a big question, but like why BMC versus maybe an abstract execution and like
Okay.
verification?
So the question is, why CBMC versus a pharmacy or another abstract interpretation system? That really just comes down to, I was trying to find the best balance between practicality and the ability for me to teach. So pharmacy is great, but it is a bit unwieldy. If you've had a chance to use it, I'm sure you know what I'm talking about. The nice thing about it is if it can't solve something with its abstract interpretation or its proof automation, it'll dump you right to like a RockQ or Coq. And that's great if you've actually studied all the process to go through it. If I'm trying to take a developer who really doesn't have much experience with formal methods and trying to get them to do this, I find that it's much easier to kind of give them a chance to kind of play around with the combinatorial explosion you may get with CBMC if you do something wrong, and then address it. It's something they can fix because all the specifications that you can see that I have in code, it's all in C. And so I don't have anything separate I have to do. I don't have to build up tactics to actually resolve these if I can't solve it directly in CBMC. I know in that case, I just need to find another way. Do I think that CBMC is better than pharmacy? No. I just think that for my purposes, at least for the work that I do, and I think also possibly for like a FreeBSD, it's easier. It's easier to deal with, it's easier to maintain, and it's also a little easier to teach. Yeah, you're welcome. Any other questions before we move on? Okay. So really, what I want to have here is it's a call to action. So I've demonstrated that we can use this today. It does work. It works fairly, fairly efficiently, and it's something that it can be taught. I would love for anyone here or anyone else to reach out if you have any questions about this or would like to get started. I'm more than happy to help. My email address will be at the end of this slide deck, and also the slide deck and the source code will be published as soon as we're done with this talk. And I'm happy to share what I've learned. I'm happy to assist. Just let me know. As far as project ideas, especially say in FreeBSD itself, if we go through and actually perform some threat modeling, we can start prioritizing where we want to look based on the severity of attacks. For one thing, obviously any areas that have a potential for remote exploits, we can verify that common attack vectors have been mitigated. And we can actually do that pretty well with the property checks in CBMC. We can verify, for instance, we don't have any buffer overruns, that we don't have any use after free, that we're properly managing locks and that sort of thing. We can also verify, some of the sandboxing stuff that's come out, like for instance, Pleasant Unveil with OpenBSD, Capsicum and Mac with FreeBSD, or even a Chaos framework and the common extension modules you see for that for NetBSD. These things we can verify, and we can actually do a fairly good job of making sure that contracts are being followed. We can also verify that there's no escapes in jails and virtual machines. And we can also talk about the layer between the kernel and user land. And are there ways that we can better protect this to reduce local privilege escalations? These are all things we can kind of start digging into. Now, I think that to do this completely, like if we wanted to completely model check, say, like FreeBSD's kernel or FreeBSD user land, that's a huge task. So what we want to do is we want to focus in on small areas and try to focus toward improvement, and make sure we have nice chunks that we can kind of pick up, verify, and then kick off. The nice thing about this is once we do this, we can kind of come back and say, hey, look what we did. We found these issues and we found this through model checking. We now have in these areas a model checked kernel. That's cool, and that's something we could do. So finally, well, I'm sure you guys have questions. I have answers. Let's see if the two match. Yes?
Is it possible to model async code, or to verify async code with these things like callbacks, continuations? I'm gonna pass you a block that you're gonna call onto later, etc.
Yeah, so the question is, can we verify asynchronous code and code with callbacks? Yes. In fact, the software that I verify professionally is very callback heavy. It actually has, among other things, it actually has its own fiber implementation. So CBMC does work with this. The nice thing about CBMC is even if there's a feature that you don't necessarily have built into it itself, you can simulate this with user assertions and property checks. And you can go pretty far down that path. A good example of that is it doesn't support the kernel locking in kernel threads, but I can translate that to something that it does do, which is pthreads and pthread mutexes and that sort of thing. And that works very well if we want to do concurrency stuff. Yeah. Any other questions? Okay. Well, thank you. This is my GitHub. This is my email. All this. You had a question? Sorry. Okay. All of this will be made available, the source code and the slides, as soon as I'm done here with the talk. And you guys are welcome to look at it. You're welcome to email me if you have any questions or want to look at this any further. Or you can even open up a PR on these projects if you really want. If you find something that we can add or something else. Fido and Mod Fido, it's really just a didactic thing. I don't expect this to become like a port. I don't expect this to be something we actually would put in the FreeBSD. It's an example I put together. It's fun. I use it for myself, but it would need actual significant work if we wanted to integrate this into something that's a real thing. We do have like MacDo and stuff like that for, and also sudo as well for FreeBSD. So probably not necessary, but it wouldn't have been a fun talk unless I had something. All right, thank you guys so much.
Yeah. All right. Hello, welcome to Through Mac and Back. The title gets more fun if you say it as fast as you can. I'm Kyle Evans. I've been a FreeBSD source committer since 2017. Kind of weird to think that it's been almost 10 years, but it has been apparently. I currently manage the FreeBSD team at Clara. We do FreeBSD and OpenZFS support, so if you're not already talking to Alan, then feel free to reach out. Marketing heavily hinted that you might be tired of listening to me after this, so they recommended I include a QR code so that you don't have to talk to me. I'm not an expert on this. I'm just one of the last few that touched it, and trying to trick other people into touching it as well. And I'll probably use jail and prison interchangeably for no reason whatsoever, so that'll be fun. So we're going to go through a little bit of the background, talk about some of the implementation, go through a few examples of how this thing flows, and then talk about recent work and the future things that I'm not going to have time for, but hopefully someone else maybe can, including a sketch of what unprivileged jails might look like. So at first, beginning, you have the almighty UID 0, privileged. In the kernel, this is SUSER, is this user root. Around 2000, this evolved. So we now have an ability to actually revoke privileges from root. And that's still maintained for quite a while until 2006-ish, I believe, when the priv interface was introduced. This broke out the privileges into many, many more fine-grained privileges, most of which kind of boil down to, they're still pretty much delegated only to root, but now you have other options. You can give them optionally with different policies. We have jail policy that can grant it to jailed root. We do grant a subset, but we don't inherently trust the jailed root, obviously. We still have the SUSER enabled knob as of this point, and it was a really good evolution. It kind of broke out things by subsystem and even more granular within subsystems. So this was a really nice addition. We have prison priv check that does the jail policy, and that's in the jail bits. We grant some based on flags. So give it a allow mount flag. It can do some mount things. You get network privileges only if you actually configure a VNet. And this is all good and very, very nice. So MAC, the name, so mandatory access control. The traditional model, DAC, discretionary access control. This is the traditional Unix permissions that everyone's aware of, whereas MAC, this is more objective. You have a subject, you have an object, and you apply a policy to it, maybe based on rules, maybe based on other things. That's kind of left up to the policy. And more importantly, just because you have access doesn't mean that you can grant others access. So this is incredibly nice. So the framework itself, it's pluggable, stackable. You can have multiple policies imposing on these same entry points, which are the hooks that policies can define. This isn't quite as convenient as the Linux version of this. It's not really sysadmin friendly by default. If you're writing a policy, you're writing a kernel module, and you actually do have to have knowledge of how the kernel works to some extent. They had tried to make it less hairy by things like if you have an object passed to an entry point, then it will pass both the object itself and the label. But obviously, that's not incredibly helpful. I mean, the label is going to be at a specific spot in the object, so that's not really removing much need for anything. I mean, it's slightly more convenient, but you still have to really have kind of knowledge of kernel internals to really be able to do anything with that. So for labels, we have a policy or the notion of slots. So each label carries 4 slots, and the slots are kind of decided when the module loads. If it has an init label hook for a specific type, then it ends up getting allocated a slot. You can have up to 4 of these. So that's kind of limiting. There's some proposals to increase that to 6, which isn't, I mean, it's not a bad idea. It's a little bit of overhead, but it's, I mean, on a modern system, it's probably kind of a drop in the bucket.
There's an option in kernel.
I don't believe at the moment, but have you? I mean, there's a macro, but you can't do this easily in your kernel config, which would be nice. But, yeah. So policies, as I said, these are actually kernel modules, which is kind of not very user friendly, but whatever. We can add user friendly things on top of this. They can be rule based or label based. For instance, like MacBiba, MacMLS, those apply labels to things, and then those flow throughout the system and apply policies to and govern access that way. You can have single label versus multi-label, so per file system or per file directory device. You can also apply labels to things like sockets, interfaces, all of the fun things like that. They implement entry points from Mac policy ops, which is a massive table of over 200 function pointers. That's not very nice, but it works. Each entry point takes a subject and object. You have a ucred, which is the identity of the thread. So it has the UID, GID, prison, and then the object. So vNode, socket, pipe, now jails. So that's you can do a lot of different things with these. Going into the implementation a little bit. So for instance, when you call kmf to read the kernel environment, you might do a privilege check, right? So is this root? What does that process look like? Breaking that down a little bit. So you do a priv check. This invokes the MPO priv check. Then it goes, if a Mac module here doesn't explicitly grant it, then we move on to the jail policy. And the jail policy applies based on, as we had said before, different jail parameters, things like this. If that doesn't, then we go into the traditional superuser policy. Is this root? There's a few things papered over there. We have some exceptions. Things we do allow unprivileged users to do in some situations, but not entirely important for this. And then if nothing else, then priv grant to escalate. So another example, so this one is just acting on a privilege, so that's interesting. This one's a little different. So this one, we have an object as well, right? So you call open, we check, want to check if this is allowed. If you have a privilege check, then that's going to go in between, or basically before Mac. So you have an opportunity to elevate privileges and then constrain them based on the context. And then proceed or deny, and breaking that down. So Mac framework, Mac policy check, it invokes, if you have multiple modules that implement this entry point, it'll invoke each one. It has a precedence for errors, so there is a defined order in which errors will actually surface from these things, and that's what Mac error select does, and then reject. So this is how the different policies can kind of work together with something like this. So labels, there's a little bit of overhead in trying to add labels to a new object. So you have at least 5 or 6 different entry points you have to add in order to actually label something. You need a init label. To do any kind of setting, getting at the to user land, you have to be able to copy, internalize, and externalize. We pretty much, when you attempt to import or export, we create a temporary label, lock things, import, export. If you're trying to set it, then we additionally check if you can relabel it. so that if you have a policy that is strictly supposed to decrease permissions, then that's the point where you can deny it and say, no, we don't want this at all. It's eperm, whatever. And then destroy label, which is maybe not the most helpful unless you've actually allocated something back into init label. Most of the time, flag bits to indicate capabilities is probably sufficient. And then for some things, entry points exist to inherit them to new resources. For instance, if you create a new mbuff and you have a label on an ifnet, you may want to propagate that to the mbuff so that you can actually restrict things there or do whatever accounting. Same thing for sockets. If a new connection is created, then you can inherit the label that way. So looking at a few examples just as inspiration for things that we can do. Mac and TPD, it's incredibly simple, right? And this has been used on most systems since FreeBSD 12. It was written by Ian Lepore, if I remember right. So NTPD up until then was running as root, and it only really needed to be able to set the time, right? That's one privilege, maybe two. So he implemented Mac and TPD, just uses MPO proof grant to allow the NTPD user, based on a configurable UID, obviously that's going to be 123 on FreeBSD at least. And boom, that's all it needs to be able to do. Suddenly, no root NTPD. It's kind of crazy that it took this long to get there, but that was, to be fair, back in 2018 or so. Another one, MacDDB. I think this one might have come from Juniper. Yeah, so this one, limit KDB so that you still have access to the debugger, but you can't quite do arbitrary things with it. There's sets of things that are labeled safe. You can still use it to inspect various things, but trying to limit it so that you can't actually expose arbitrary memory. It's kind of nice, and this is a good example of constraining the operator from doing things, which is a very useful use case for the Mac framework. You don't have to just elevate unprivileged users. You can also smack root down a little bit. And then our final example is going to be object access control with BSD extended. This is the file system firewall. This one's really nice. It's incredibly flexible. The man page is kind of a mess. There's a lot of different policies you can impose. There's also work in progress by Martin Krakauer. He's trying to extend it so that you can do wildcards, which is kind of nice. And this is a good example. It uses pretty much every vnode check entry point that we have to offer. It's kind of crazy, and I'm sure it's missing something at this point, but we should probably audit that. It's a good example if you need something that's working on vnodes or most objects. So going into recent work. So MacDo. This is pseudo alternative. You do not need a setuid binary for this. We have rule sets. You can define when escalation is allowed, when it's not, which transitions are allowed. It's the set of entry points it implements is actually relatively minimal. And it's still a work in progress, although it's incredibly functional and a very nice work in progress. It uses priv grant to allow set cred, and then may reject it later based on the specific context that you get from cred syscalls. There's also the jail integration that I did. So naturally, jails are a part of the ucred, so you can reject actions based on whether the calling thread is in a jail or not. But what if we wanted to actually operate on a jail, right? If you wanted to not deny or allow creating a jail or setting a certain jail property or things like this, that's not a thing that you could do up until recently. So now jails are actually a first-class Mac object. We added a label to struct prison, You can use jailget jailset to fetch it with as mac.label. We added 7 new entry points in the process, not including the 6 for label boilerplate. Added checks so that you can deny attaching, removing, things like this. And it's all really nice. You can propagate labels with created, cleanup, and all of this fun stuff. There's a motivating example here, and we have to go into a little bit of context here. So the traditional jail model, you have, in this case, we have Steve, right? Steve is, we'll call him the operator of the machine. He creates this jail. It has this workload that just, manager process, a few processes spawned, and it's running happily. There's a lot of holes in this jail though, right? Steve can signal anything inside of it. He can view it all. He can debug any of it. That's great. Up until recently, Steve could also do this if he wasn't privileged, as long as it was a matching UID, which kind of violates a lot of people's worldview of how these kinds of things work. You don't expect that UID 1001 on the host could do anything with the jailed process with the same UID. But fortunately, we did work to address that. So what if you take this and try to limit the number of things you can do? So now instead of allowing Steve to do anything, he can only talk to the manager, right? Can't signal, can't debug, anything like that. Can't touch the file system. This is what I'm calling a capsule. So you seal jail, create a capsule, and it must be no persist. If it's going to shut down, it needs to do it itself, or you need to be able to do it with the manager. This obviously isn't great. You might need, there's a lot of ways that could go wrong, so the manager needs to be really robust. It's not really designed for general workloads, just for very specific things that are tightly integrated. It rejects most things across the boundary. You can still maintain, a socket across there so that you can control it that way. Try to deny pretty much any VFS operation across it. You can't mount into it. You can't do any of these things. It's still not something that I consider safe. I mean, it makes me feel better about the things that are running in this jail, that their environment isn't going to change out from underneath them. And it's something that's actually possible now that we have these jail things. And more importantly, I surfaced this on a mailing list and no one else really liked the idea. So now I can keep it to myself and be happy. So the things that I'm hoping I can convince someone else to work on, among other things. So ZFS. So we have this notion of delegated permissions. So you can delegate things like snapshots rollback to unprivileged users. But it'd be really nice if we had some way to integrate these in Mac so that they can actually be rejected. Today, I don't think this is very easy, or not an easy way, or not in a way that isn't incredibly ugly. Ideally, these things would have the entire pool dataset context, which isn't, it's just looking at ZFS octal.c where this is implemented. It's not really easy to get to the context from there, so that requires someone with more ZFS know-how than I. But there's an additional challenge that we have this table with 274 operations. If you suddenly try to expand this to include ZFS things, you're now bloating it up. You're probably going to have at least 300 by the time you're done with that. And these last 10, 15, they're not going to be used by anything except ZFS. So is that something we really want to include in this? I don't know. I mean, I think it could be useful to consider how a module can bring its own entry points, but then that has its own problems with lifetimes and things like this that kind of need some careful thought. I mean, especially because you could imagine a module that does things, and if the file system does provide these things, then maybe it wants to use them, maybe it can function just fine without it. I mean, it needs some more design work for sure. Moving into unprivileged jails, which I call this MacU jail, just because that feels like a really nice name. There's reasonably high demand for unprivileged users to be able to create functional jails. And when I say functional jails, it's really easy to do the thing like we do with unprivileged root, where you just say, okay, if you have no new privs, you can create a jail and you have your own UID inside the jail, but that's it. That's not really useful. They want to be able to do things with the file system. They want to do things that require slightly more privilege, and that requires more work, right? You can't just leave them with basically a CH root, because that's not going to do anything for things like rootless podman, which, yeah. So we have user namespaces, which are a beloved concept. It's not kind of a security nightmare, but I think we can do better. It's because we can tie these to the jail. The jail is already something that we don't really trust, right? We grant it a subset of privileges based on the things that we allow the jail to do. And with Mac, we can constrain that even further. We can say, okay, this user can create a jail with this set of UIDs, this set of GIDs, and maybe they can set these jail parameters, maybe they can't set these ones, or maybe we force them to set these ones. I only want this user to be able to create jails if they create VNet jails. These are sensible restrictions, and it seems like we could do even better with more fine-grained privilege restrictions, which we actually have a project probably coming up to upstream this thing called Mac BSD priv that would allow arbitrary privilege assignment and revocation. So it could play well with that, but it could also be that you want something more integrated into UJail. I don't know. It's one of those things that needs to be worked out. But the key is you translate the UID, GID at the kernel boundary. So internally in struct ucred, we still track it as the unprivileged UID, right? You don't want someone to be able to create a file with the real UID 0. That's not great. So we instead, it keeps the real UID, GID that are unprivileged, and we instead elevate it for the things that it needs to do. And there's still, like, some of the things we would want already exist, right? So the ones in green here, those are things that exist today. We don't have a vopstat post or a vnode post stat that you would probably want to do to translate these parts. There's probably additional entry points that would be useful for this, but I haven't tried to enumerate all of these things, just kind of give you an idea. Ideally, things like file UID, file GID, all of this is the real unprivileged user. If you encounter a file that the host dropped into the jail that has something outside of that range, you just remap it to the invalid entry, so basically nobody within the range. And then that's somewhat clean. And then you can impose additional restrictions on those. But this model, I think, is a little bit better than the user namespaces on Linux, at least. And it's the downside is it kind of puts the responsibility to avoid escalation in some cases onto the sysadmin. But I think in some sense, as long as this is well documented and we provide the tooling that's needed, then I don't think that's really a problem. We just have to be honest about the trade-offs that you're taking when you try to do something like this. Very early finish. Questions?
So if you create an unprivileged jail, and in that jail as user 1002, you create a file, who owns the file when you look at it from outside the jail?
So if you create a file inside an unprivileged jail with UID 1002, who owns it outside of the jail? The unprivileged user that it maps to. So UID 1002 in the jail and its UCRED instead has probably something off in like the 51,002 range. And this is what actually gets sent to disk, and we don't have to do anything. We wouldn't try to translate that, right? That stays in the UCRED like this, so that it tries to fail safe.
So how does that work when you're doing the VFS access control?
How does that work when you're doing the VFS access control? So that's where check access and all those come into play. So those only actually allow the operation to succeed if the remap works.
Right? That's what makes this a lot better than the Linux one, which tries to do all the mangling back and forth in the VFS layer and trips over itself every other.
Yeah, I think that's a better model.
Is
Anything?
our UID space big enough to go past 65,000 for the unprivileged set? To allow each user to have their own 65,000 UID.
Is our UID namespace big enough for this? I don't think so, but
Can we consider making it big enough that every user can have their own 65,000 unprivileged UID?
can we consider making it big enough so each unprivileged jail could have 65,000 UIDs? I mean, I would imagine so.
Wouldn't that require a large number of system calls to change because UID would need to be bigger than 16 bits now, and that ripples a place or two?
Wouldn't that be incredibly painful? Yes.
Could? Yes. Easy? No.
Yes, it is possible, but it would not be easy, and everyone would be angry, but it would be better.
It wouldn't be the first time everyone was angry.
Yes, it wouldn't be the first time everyone is angry.
Maybe you could get away with 60,000 UIDs per jail and have another bit used to index it, so you're not actually having to multiply the UID space.
Right. Maybe you could get away with indexing these things differently. Yeah. Yeah. I think there's some good options there. Yep.
Not the question I was thinking of at first, but because of those two questions. So then maybe you're thinking of UID changing to a GUID.
So thinking of UID changing to a GUID, no.
That would solve that problem.
Would it?
You had an early example showing like NTPD having the permission model for that to run that without root, but you had it specifically tied to a single UID. Was that specified in the kernel? Because you said some of this was like kernel modules.
So the NTPD example was that tied to, or the UID tied to a specific. So it's exposed as a sysctl.
Yeah, 'cause the only reason I'm asking is because like other NTPs, like Cronny or whatever, has their own users, and like other capabilities will have their own users rather than the ones at base.
Right. For Cronny, you can change it so that Cronny could also elevate the same way with the same module.
Okay.
I mean, that does kind of make the name nonsensical, but it works.
What kind of visualizations or debugging exists for this whole layer? Coming in from somebody who's run FreeBSD but doesn't hack on it regularly, if I wanted to look at how this was done, that's a lot of like, this layer talks to this layer, talks to this layer for certain things. Is there anything that you guys have from a development perspective that would help me understand how this works architecturally?
So, is there any kind of visualization or anything that would help understand how the Mac framework and all the layering works? Not really.
The question I was thinking of asking at first was, so there's no module that delivers a text file of configuration for Mac. This is all software.
So the question is there's no text file that delivers a configuration? No, but there can be. It's up to the policy. So the policy chooses how it's to be configured. It can be configured by text files. It can be configured by, I mean, if you take an example like variexec, I mean, VariExec has manifest that it loads and a kind of complicated control interface. I mean, I guess probably not that complicated, but it exposes the configuration through things like that.
Yeah, you can set Mac labels via VariExec.
Yeah.
So the Mac grant by label, Mac module uses labels set by VariExec to allow control privilege escalation.
Okay.
I think a good example is your which GIDs can see a process thing that we did recently.
The which?
The one for the company with a V that lets you set more than one GID can see all the processes.
Oh, yes, yes. We had done, so we have Mac see other UIDs. And this one, you can specify a single, or historically you could specify a single GID that can see everything else on the system, but a recent change we made was to take an array instead, so that it can. The problem is if you only have one GID and you want to do multiple daemons, for instance, to be able to see other UIDs on the system, then suddenly you're doing janky things like, now I have a group that just organizes all of these things that can see everything else, and that creates another point of shared access. And that's the kind of thing that's probably harmless, but it doesn't give me warm and fuzzies. So we changed that so that you can specify multiple groups, which is much nicer. Yep.
So I'm just curious if there's any thought to maybe like a bit of recursion in unprivileged jails. Like if I want to create an unprivileged jail in an unprivileged jail, does the ucred still reflect like the upper original host UID GID bits?
So the question is, in the case of nested unprivileged jails, what does the ucred reflect? I think it would reflect. I think you don't allow that. I think you don't create subjails of unprivileged jails. I think yeah. Yep.
Real quick, I just checked. Tell me if I'm wrong, but UID is already 32-bit.
It is.
Ah, yes.
I just created an
It's-
account that was like 32 to 32 minus 1,000.
I must be thinking of a different platform. So the UID is already 32-bit wide, so this is good.
Okay. I was like,
I got a question about lower handed groups. So this is what you call functional unprivileged jails.
Mm-hmm.
What about non-functional? So basic, very basic situation which many people have. You have application that you do not trust. You want to run it from your UID, but as simple as possible. And actually this utilizing the feature that you call the bug, that within the jail, if UID is much, you have the access.
Yeah.
So, how close we are just to enable me to run some binary that I don't trust in a very restricted jail without utilizing sudo or monkey?
Yes. So the question was about what I called not as useful. So the equivalent of unprivileged chroot. I mean, I think this wouldn't be a lot of work. I think if you're going to do it, then you still want some of the other advanced configuration I talked about. Like you want to still be able to set which jail parameters that are allowed. So I mean, you still need some of the things from this, but nowhere near as much. I mean, you pretty much need the second bullet point there. But other than that, it's incredibly easy to allow something like that. I mean, you still do no new privs. The thing that I called a bug is actually configurable on the jail. So with the configuration, you would just set that. I think we called it allow unprivileged parent tampering or something like that, which would obviously be really safe in that instance because the unprivileged user creating the jail is the only one that's going to be able to signal other than root, obviously. So that would be incredibly, or relatively easy to do.
Any chance to have it in 16.0 release?
Any chance of doing this in 16.0? Probably not, at least not me.
So
a sysadmin who wants to run secure services on FreeBSD but might lack kernel knowledge, like me. How much Mac awareness would you recommend?
So, sysadmin not wanting to write policies, how much Mac awareness? So that's a bit tougher because most of the policies we have now, I mean, you have things like VeryExec, MLS, BIBA. These things are more friendly, but as far as the framework itself goes, like there's probably not much there. I mean, you obviously need to. I guess it's going to kind of depend on the policies you want to deploy.
One of the problems with having the Mac stuff too easily configurable is it's too easy to screw it up and it's too easy to bypass it. So for instance, that's why with Mac VeryExec and so on, we have it all extremely tightly controlled so that you know exactly what you're getting. That's one of the problems with SE Linux, I think, is people when they try to configure it, they screw it up.
Simon notes that easy to configure is easy to screw up.
That's kind of like why SEBSD was given up. It was working out before.
Yeah.
It's just there's too much stuff to cover when to try to consolidate it into one policy.
Yeah. Yep.
I think, question more of a comment on that. I think the best way to fix that would be to come up with some sort of max-add, something where we can take a look at the actual policies. And, when we do configure them, what are we gaining, what are we losing? And if we can make that as complete as possible, then that would allow us to at least be able to find trivial and, common mistakes.
Anything else? All right. Thank you much. Okay.
The first one is, you looked at FreeBSD 7 UMath FS.
I have not, but I've heard it's cursed in some way. And it's notably gone, so I imagine there's a reason.
The other one was, why not extend the UID GID namespace to 32 plus 32 bits? So I guess 64 bits wide, not for half. And then put the JID in the upper 32 bits.
So why not extend the UCRED to 32-bit plus 32-bit? Yeah, it already has a jail pointer, and you could changing struct UCRED is kind of painful. We've found this out recently with trying to fix the effective GID situation, because FreeBSD still did the CR group 0 was the effective GID, and so this caused a lot of problems at set groups and get groups. The effective GID was exposed there and also set there, so it was mostly painful because most of the software is ported from somewhere else that doesn't do that, because it's pretty much us and Mac OS, maybe Illumos as well. But yeah, we're few in that camp, so that's the kind of thing that suddenly you set groups thinking you're only setting supplemental groups, and your effective GID changes. This actually there was a bug in OpenSSH around that as well on FreeBSD. When it tried to do privilege dropping. Anything else?
So related, can we put JLID in the XUCRED already?
Can we put No, we can't. The question was, can we put JLID in XUCRED? The XUCRED we can't change. There's too many expectations around it, and I got yelled at the last time that I almost tried to change it. So. And that was before even actually proposing a change. So, okay, thank you much.
going to wait for them to say go. Thanks everyone for being here this afternoon. Really appreciate seeing so many nice faces. Oh, there's my roommate, Rob. My sleep deprivation is not his fault. He's been a great roommate. Really friendly bunch of folks here at BSDCan. We're all set? All right, thank you very much. I'll get started then. Hello, everyone. My name is Corey Steffen, and you're about to hear the weirdest introduction of anybody at BSDCan. Currently, I serve as lecturer in religious studies at the University of Houston, course developer and instructor of in the THD program, so a doctoral program in theology at St. Leo University in Florida, and instructor of theology in the core curriculum for undergraduates at the University of St. Thomas in Texas. My academic background is in Catholic historical theology, particularly the thought of the great thinkers of the early church, whom we call the Fathers of the Church. I'm proud to share that I have a newly published historical monograph with the Pontifical Institute of Medieval Studies, which is based here in Ontario, that is titled Maximus the Confessor's Thomistic Legacy. And my roommate for this conference told me that he looked up my book before we crossed paths, so I guess it's already getting out there. In my current combination of adjunct teaching assignments, I work in the traditional liberal arts, not computer science, actually. So at a computer science conference that is full of oddballs, I'm probably near the top of the bunch. In my talk at BSDCan in 2023, which was titled BSD for Researching, Writing, and Teaching in the Liberal Arts, I consider the BSD operating systems as professional tools in zones in which they are only rarely discussed. I propose that 5 areas in which the BSD operating systems excel make them particularly well-suited for the work of students, educators, and scholars in the liberal arts. First, openness. Second, documentation. Third, stability. Fourth, security, which in academia actually mostly means privacy. And fifth, academic third-party software package availability. In my talk the subsequent year at BSDCan in 2024, which was titled Summa Tetraodontidae, Summa of the Pufferfish, Thomas Aquinas Explores OpenBSD's Medieval Orderliness, I looked at the internal arrangement of the OpenBSD operating system and the OpenBSD project as being intentional and consistent enough even for an ever-persnickety 13th century Dominican friar. More or less drawing on the structural pattern of Thomas Aquinas' Summa Theologiae, I imagine Thomas himself asking and answering a hypothetical series of questions about OpenBSD, all, of course, in good fun. Today, I will do something similar to what I did with Thomas Aquinas, but I will return to considering FreeBSD, OpenBSD, NetBSD, and DragonflyBSD together as a family of operating systems, taking seriously their common ethos, as it were. My talk for this BSDCan, BSDCan 2026, is titled Escaping Plato's Cave with Software Freedom, a classical Greek symposium with Fred, Puffy, and Beastie. I have modeled much of this talk after the timeless dialogues of the great, if not greatest, Greek philosopher Plato, cheekily adopting many elements of Plato's beloved style. I will depict the mascots of DragonflyBSD, OpenBSD, FreeBSD, and NetBSD as engaging in an imaginary conversation based on Plato's famous allegory of the cave. The mascots who will make up my dramatis personae are, of course, Fred, the dragonfly of DragonflyBSD, Puffy, the yellow pufferfish technically a blowfish, but anyway, of OpenBSD, and Beastie, the friendly trident-bearing demon who is officially the mascot of FreeBSD, but basically also part of the iconography of NetBSD. And yes, the NetBSD logo is a flag, and NetBSD does not actually have a mascot. I verified this in the official IRC channel and Libra chat before the conference. But folks, flags cannot speak, and NetBSD artwork often includes the BSD demons, so for the purposes of this talk, let's just go with Beastie. Instead of staring at a mere shadow of reality, as those who are stuck in the cave do in Plato's Republic, Dragonfly BSD's Dragonfly Fred, OpenBSD's Pufferfish Puffy, and FreeBSD's and NetBSD's Demon Beastie will discuss how persons are trapped in software non-freedom with spyware, malware, and all the rest, unless they can embrace open licensing and orderly communal coding. My guiding thesis is that the Berkeley software distribution-derived operating system family is overtly liberating in character, allowing users to live outside the 21st century iteration of Plato's cave that is software oppression. After all, BSD code is fully open. This talk will be about the nexus between two seemingly unrelated realms of excellence, one being Berkeley software distribution-derived operating systems, together with free and open source software in general, and the other being Plato, together with classical philosophy more broadly. Whether you are a BSD hacker who would not mind receiving a metaphorical pat on the back for the hard work that you do from someone whose occupation is totally different from yours, or a more modest geek like me who happens to enjoy fiddling with software as something pleasurable and ultimately beneficial for work through different pathways, I hope that you will appreciate something of what I am about to share. Above all, I hope that all of us will have some intellectual fun. Plato is the timeless universal nickname, meaning broad, though we do not quite know why, for an ancient man whose real name was Aristocles. This Aristocles was born in about 427 BCE in Athens to one of the great city-state's wealthiest and most politically active families, albeit a family whose legacy is stained by its involvement in movements among the elites to terminate Athenian democracy in favor of a rigid oligarchy. As a young man, Aristocles, Plato, was drawn to the trouble-rousing street philosopher Socrates, and Plato and his older brother Glaucon became two of the closest pupils. Oh. Let's go like this. Two of the closest pupils of Socrates. Eventually, Plato founded the Academy in Athens. This school originally was called the Academy because of its location in a grove of trees that was sacred to the classical hero Academus. But the school named after that grove of trees became so important in the history of Western education that its name begot many subsequent words that we associate with schools and learning across European languages. An obvious example is, of course, the English noun academy itself. Plato, formerly Socrates' student, became the teacher of many, most notably Aristotle, and Aristotle in turn became the teacher of many, most notably Alexander the Great. The direct lineage of Socrates teaching Plato, teaching Aristotle, teaching Alexander, generally is regarded to be the most important direct lineage in the entire history of Western intellectual activities. If Socrates had not taught Plato, and Plato therefore had not established the Academy, and if Aristotle had not therefore studied at the Academy and eventually taken its lead, and if Alexander the Great had not gone to the Academy and studied with Aristotle, and if Alexander had not subsequently conquered the entire Mediterranean world, bringing the learning of the Academy in Athens with him, then Western academic inquiry would not exist as we know it. We probably would not have a BSDCan, a conference at a university, a place that is itself a descendant of Plato's Academy, about a family of operating systems whose progenitor was developed by scientists working in a lineage of inquiry that we might trace, however indirectly, back to Socrates, Plato, and Aristotle. Aristotle's musings on the natural world became the whole basis, after all, for the modern scientific method. Of these three philosophers, Socrates, Plato, and Aristotle, Plato's surviving writings are the grandest. I don't say best, just grandest, okay? We do not possess any writing of Socrates' own hand, and Aristotle's surviving writings, brilliant and timeless though they are, seem to be akin to formalized lecture notes. They've always made for great study, but they've never made for great reading. Plato, however, wrote elegant, masterful treatises in Greek that has shaped how all Western academic writing is done, owing not only to the vast spread of translations of Plato's works through the ages, but also to the basic fact that all Western academic writing is ultimately beholden to Plato's legacy. You heard it first from me, folks. Our own Michael Lucas is basically Plato. According to what little and unreliable records we have, Plato proved himself to be gifted in both mind and writing from a young age. Before Plato interacted with Socrates, he wrote plays, specifically tragedies, none of which have survived. But his encounters with Socrates prompted him to abandon the path of the playwright in favor of a life of philosophia, philosophy, that is, the love of wisdom, the pursuit of all truths, and ultimately the pursuit of the central truth of reality as such. The main genre in which Plato wrote philosophically, or at least the main genre that survives for us, is known as the dialogue. Each of Plato's dialogues is indeed, as the name will come to us, a conversation, but an imagined one in which two or more persons engage in a respectful debate about the truth. The main character through most parts of Plato's dialogues is a recreation of his teacher, Socrates, but the interlocutors whom Plato fabricates for Socrates are not mere foils. They engage Socrates in frank, deep discussions. Plato's best-known dialogues include the Timaeus, which is about the good, that is, God and all that exists. The Laws, Plato's final, longest dialogue that covers a wide variety of aspects of law, social order, and governance. And of course, the Republic, the dialogue that has inspired me to deliver this talk. The titular noun of this dialogue that has inspired the talk for today, Republic, that is res publica, public affairs, is an ancient Latin translation of the Greek word politeia, meaning government, as in the management of the affairs of the polis, the city-state. In this discussion about society, social order, and governance, which Plato wrote roughly in the middle part of his career, an imaginary recreation of Socrates discusses justice and human flourishing with various Athenians and foreign nationals. Through these discussions, Socrates ultimately decides that Kallipolis, the beautiful polis, the hypothetical utopia, would be a place ruled by philosopher kings who would turn entirely to reason and wisdom in all decision-making. Socrates stresses the total importance of philosophy to build an ideal society. And when I teach this for my undergraduate students, I make sure to point out how convenient it is for a professor in any discipline to say, well, my discipline is the basis of a good society. One of many stopping points in Plato's Republic is the all-famous allegory of the cave. The allegory of the cave constitutes a rather small part of the seventh of the Republic's 10 books. Here, Socrates is in the midst of a long back-and-forth discussion with Glaucon, Plato's older brother, who had studied under Socrates with him. I will quote just a part of this small allegory of the cave in the translation by a faculty member at St. Bonaventure University in New York that is available for public download on that university's website. No copyright infringement here, folks. Socrates says, "At this point, I will show you something about the nature of education and ignorance. Picture the following in your mind. Imagine human beings living in an underground cave-like residence. Its entrance opens up to the light and reaches all along the cave. They have been there since their childhood, their ankles and necks chained, unable to move or turn their heads, forced to look ahead. The light from a fire blazing at a distance comes from above and behind them. Between the fire and the prisoners, there is a raised walkway. Imagine also a low wall built along the way, similar to the screen that divides puppeteers from the audience and allows them to show puppets over it. Glaucon, Plato's brother, replies, I picture the scene. Socrates says, now imagine that people walk behind the wall and carry various artifacts that extend above the wall. These artifacts include carvings of humans and other animals made of stone, wood, and other materials. Some of the people carrying these objects are talking while others are silent. Glaucon says, you paint a strange picture and describe strange prisoners. Socrates replies, they are like ourselves. Now, do you think they see anything else except their own shadows, or the shadows of one another, which light from the fire casts onto the opposite wall of the cave? Glaucon asks, how could they see anything else if they were forced to keep their heads still for their whole life? Socrates asks, and what would they see of the objects that are being carried? Would they not see only shadows of them as well? A few lines later, Socrates states, such prisoners would think that the truth is nothing but the shadows cast by the artifacts. A while later, Socrates explicitly explains this allegory. Now, dear Glaucon, the prison house stands for the visible world. The light of the fire in the cave represents the power of the sun. And you will not miss my intended meaning if you interpret the journey upwards and the sight of the things that are above as the ascent of the soul into the intelligible world, for this is what you wish to hear about. In the world of knowledge, the idea of good appears last of all, and we are barely capable of seeing it. However, when we do manage to see it, we conclude that it is the cause of all that is beautiful and right. It gives birth to light and to the Lord of light in the visible world. And in the intelligible world, it rules itself and is the source of truth and intelligibility. All right, back to me, Corey. In Plato's reckoning, as he places on the imagined mouth of Socrates, we all default to living in the cave, seeing only false images or imitations of reality rather than what is really real. In order to see what is real, Socrates explains later, we must be forced out of our dark shroud of ignorance by way of rigorous education with a special preference for philosophy. All right, I've spent some 10 minutes blabbing about classical philosophy and quoting Plato's Republic at a conference about BSD Unix. All right, where are we going? What I suggest to all of you is that one manifestation of Plato's cave today is software non-freedom or closedness, which we also might call, depending on context, software oppression. Software freedom or openness, as it might be most broadly understood, is, I suggest, the antidote, the way out of the cave, and a reality in which one might live with more philosophical rectitude, more wisely in our digital age. Here I simply speak of software that is fully open source with zero use case requirements for the end user. I speak of no less than this, but also no more, a kind of ultra-minimalist reduction to the common core of what is envisioned by the well-intentioned authors of the BSD, MIT, GPL, Creative Commons, and other Libre licenses. I'm taking a step back in regarding all fully free and open source software as truly open intellectual property. For perverse pleasure seeking in debates about IP licenses, head to the mailing lists. In a hypothetical Berkeley's republic, we might find Fred, Puffy, and Beastie discussing software non-freedom or closedness, similarly to how Plato depicts his teacher Socrates and brother Glaucon discussing the cave in the original republic. Since Beastie is effectively the original BSD mascot, and here I'm using him as a stand-in for both FreeBSD and NetBSD, two major BSD operating systems, I will let Beastie take something like the role of Socrates. Beastie says, I will show you something about the nature of openness and closedness. Picture the following in your mind. Imagine human beings living in an underground cave-like residence. Its entrance opens up to the light and reaches all along the cave. They have been there since their childhood, their ankles and necks chained, unable to move or turn their heads, forced to look ahead. The light from a smartphone's display at a distance comes from above and behind them. Between the spyware-laden product from a multi-billion-dollar tech corporation and the prisoners, there is a raised walkway. Fred, flying above a pool of water, and Puffy swimming in the pool, together reply, "We picture the scene." Beastie continues, "Those people are like us. By default, we go about our lives in a context in which we do not own our computers and other digital technology, but rather our computers and other digital technology own us. We are unaware, however, that this is the context in which we are living. We must be taught that there is a better way, the way of software openness and freedom." All right, back to me, Corey, again. There is, of course, more to leaving the shadowy, fake computing light of the cave and entering the brilliant, real computing light than the most important move from software closeness and non-freedom to software openness and freedom. Another point that should be high on our list of consideration is that of community. In this next section of our hypothetical Berkeley's Republic, Beastie again will play something like the role that Socrates plays for Plato. Beastie says, "In the world of open source software, a single person of any background who has reasonable access to the World Wide Web may in fact contribute to a given piece of open source software, whether by submitting code, donating money, providing detailed bug reports, making suggestions, helping others use the software, or otherwise." Puffy replies, "What you say is true, O demon, but what is the best place to find community?" Fred answers before Beastie, "I think, O pufferfish, that the demon will agree that we ought to turn to the mailing lists." Beastie smiles and says, "Verily, the mailing lists are our sacred texts." Fred and Puffy nod in agreement. Beyond the mailing lists, one may join conferences like BSDCan, discussions in GitHub, and other exchange places for code and software development, and my personal favorite, Internet Relay Chat, IRC, which I'm monitoring, by the way. I'm going to make sure that anybody in that Libra chat room gets your questions answered. To participate in the discourse that makes free software freeing and projects like the BSDs improve over time. It would be hard to exaggerate how essential, exciting, and universally beneficial the communal aspect of open source software really is, despite the fact that it can be tiresome. Here, as a scholar, I might think of the fabulous Zotero project, which is arguably the most useful academic citation manager in the world, precisely because it is designed by academics for academics, with academics continually in conversation with each other about how to make it more useful. And that's in the FreeBSD ports tree at this point in time. Turning back to BSDCan, I might think of this gathering itself as the kind of environment in which we build community, from hallway chats to question and answer sessions like I hope to have at the end of this talk, to impromptu group meals, to the 24/7 Hackers Lounge, where folks seem to be reminded that shared creativity happens the most organically when we humans interact face to face. Community makes doing some task for work or hobby pleasant, but it also makes having meaningful standards in that task possible. If the past few years have revealed anything in the operating system space, it is that those of us who have been cautioning for a long time that proprietary operating systems inevitably would fail from their lack of community and therefore standards were correct. What can we here at BSDCan say about standards, and what standards, if any, do today's BSD operating systems share in common? For the sake of diversification, Puffy will play something like the role of Socrates in this next excerpt from Berkeley's Republic. Fred says, "My friends Beastie and Puffy, we all know that it is essential to have high standards of code. What standards matter to you and why?" Beastie replies, I know a great deal about this, but I would find it enlightening to hear our pufferfish friend speak first. Puffy says, "Thank you, O dragonfly and O demon. Yes, I shall speak. The best software has documentation atop documentation atop documentation. Poorly documented operating systems cannot withstand the skepticism that is standard, say, in modern academic circles. Organization and documentation in turn go hand in hand. An operating system whose developers prioritize consistency probably will be intelligible for the person who takes the time to learn a bit about how it works. Good manual pages and a clean handbook or guidebook that a dedicated user base actively maintains, this duo is the minimum of order that a rightly arranged operating system ought to have." After pausing to think for a moment, Puffy continues. "Here, friends, I repeat what Michael Lucas writes in the introduction to Absolute OpenBSD, 2nd edition. Documentation errors are considered serious bugs and are treated as harshly as any other serious bugs. When I look at each of you, Fred and Beastie, I see similar attitudes, albeit with your own approaches. One of the first lessons, and surely among the most valuable, that one learns while studying all 617 pages of Lucas's Absolute FreeBSD 3rd edition, as I've heard that some weird Dr. Corey Steffen guy has done, is that to discover anything about how to use a BSD operating system, the right place to turn is almost always the official documentation. In the FreeBSD realm, the officially promulgated handbook ties together the ever-useful manual pages in an elegant fashion, and the same can be said for the guide in the NetBSD realm, the handbook in the Dragonfly BSD realm, and the officially curated frequently asked questions, FAQ, in my own OpenBSD realm. Fred interjects. Indeed, Puffy, learning how to make a desktop operating system bend to one's professional requirements is easier with any of the major BSD operating systems than with most others, certainly than it would be with every non-free, closed operating system. Beastie replies, "You have spoken well, my friends, but what about code correctness and therefore system stability?" Fred responds, "I too shall quote the introduction to our great teacher, Michael Lucas's Absolute OpenBSD. Every skilled programmer knows that programs written correctly are more reliable, predictable, and secure. In the BSD operating systems, development models differ, but each of us follows at least one central idea: do not fix what is not broken." Beastie says, "Right. IFconfig is still what controls a host's network connections, even though networking is different now than it was 40 years ago, in 1983, when 4.2 BSD was released, and along with it, that first iteration of IFconfig. Whereas other operating systems, especially non-free, tend to undergo massive overhauls without obvious necessity, BSD development teams prefer to fix and mature their utilities rather than replace them entirely." Puffy responds, "Right. And when wholesale replacements do happen, they are for code correctness, security, and/or functional utility, never flashiness. Here in OpenBSD, for example, Theodorat has stated for the record that he believes that overhauls are worthwhile when they are necessary for security or other correctness, but not otherwise. And in Dragonfly BSD, surely you, Fred, could tell us of how Matthew Dillon and crew state explicitly on your website that they have, quote, no reservation about cutting ties with legacy when it makes sense. But of course, that's only when it makes sense." All right, back to me, Corey. "In recent years, I have witnessed something that strikes me as not entirely in keeping with the principle that we ought not fix what is not broken, namely the rise of the so-called ethical software or ethical source movement. It is reasonable to expect persons in a voluntary project to default to the assumption that each person in the project both means well and has something valuable to contribute. These are two basic principles for interpersonal discourse that I reiterate throughout my freshman classes in subjects as disparate as Catholic theology and the secular history of world religions, especially when I assign group formal debates. Always assume that an interlocutor has the best intentions and that the interlocutor is working with his or her best application of reason. I'm not going to claim that the ethical software movement is inherently wicked or some such thing. Not here to do anything like that. And I acknowledge that it is probable that a few folks right here at BSDCan participated in it, right? Yet a problem with the rise of the ethical software movement that I've identified has been that some of it, perhaps ironically, is antithetical to openness as such. Some persons have grown quick to say, let us keep out the bad people. No sensible person would hear that and reply, no, stop. I want to go out of my way to work with bad people. Yet, I'm compelled to ask, what happens when the precedent has been set that persons may be excluded from projects that have nothing to do with certain ideologies on the basis of those outside ideologies? Here we return to our hypothetical Berkeley's Republic, allowing Puffy, Beastie, and Fred to discuss why we ought to exchange intellectual property openly wherever it is viable to do so. Beastie says, with each of the BSD operating systems, everything is written internally by one project team, one for FreeBSD, one for OpenBSD, one for NetBSD, one for Dragonfly BSD, and so on. Most things, therefore, are internally intelligible. Everything is open, which means, as Michael Lucas writes in Absolute FreeBSD, nothing is hidden. You can see the innards, warts and all. Fred interjects, indeed, our licensing is truly open. Anybody can do anything with the code. Yet, my friends, might this actually be dangerous? Puffy retorts, yes, of course, open licensing can be dangerous. It can lead to abuses of all kinds. Yet open licensing also can be liberating. It is difficult to have the good without the bad. Fred asks, how so? Beastie suggests, consider, if you will, a time and place in which there is critical censorship of intellectual activity, including in the digital sphere. Perhaps some totalitarian regime is blocking access to university research databases. Or perhaps some particular democratically elected government is prohibiting some form of speech. Or worst of all, perhaps some university's information technology department is blocking port 22. Or perhaps, Fred interrupts, I see. In a time and place with censorship, the only way to engage safely in intellectual activity in the digital sphere would be to use truly open software. Such software can be trusted because it can be audited by anyone, and it has zero ideological or other requirements for the end user regarding how he or she might employ it. A whistleblower, a professor, an attorney, or a journalist might turn to such software out of necessity, but it seems best to be prepared with such tooling, even in a time and place in which censorship is modest or non-existent. Puffy adds, openness, my friends, ought to be considered a philosophical category. Our copyright policy webpage on openbsd.org begins with this line, copyright law is complex. OpenBSD policy is simple. OpenBSD strives to provide code that can be freely used, copied, modified, and distributed by anyone and for any purpose. Turning to NetBSD, we might quote a nearly identical ideological stance from netbsd.org/about. The NetBSD project provides a freely available and redistributable system that professionals, hobbyists, and researchers can use in whatever manner they wish. Beastie has not made the FreeBSD website so explicit, but FreeBSD's two-clause BSD license nevertheless implies either a similar or identical collective stance. Redistribution and use in source and binary forms with or without modification are permitted. Are not permitted, but rather are permitted as a permanent, unassailable fact. Beastie says, right, friends, our code is open because it ought to be open. No strings, no ethical requirements, simply open for contribution, study, adaptation, adoption, and usage. Back to me, Corey, again. To close our imaginary Berkeley's Republic, I would like to hear Fred, Puffy, and Beastie return to the allegory of the cave from Book 7 of Plato's Republic. As before, Beastie will play a role like that of Socrates, drawing on some of the actual language that Plato places on the mouth of Socrates in his Republic. Beastie says, someone might wrongly contend that software non-freedom or closedness is superior to software freedom or openness for two reasons. The first is when someone leaves closedness and enters openness, and the second is when someone leaves openness and enters closedness. When someone first steps out of closedness and into openness, that one might be uncomfortable, largely owing to lack of familiarity. When someone makes the opposite move, stepping from openness into closedness, that one might think that the comfort of certain things working automatically that do not work automatically in openness makes closedness the place to stay. Fred replies, I have seen both. Puffy nods in agreement. Beastie says, it seems to me that what we need to do is work together to show others that the minor inconveniences that come from stepping out of the cave of software non-freedom and closedness and into the light of software freedom and openness are entirely worthwhile. Fred replies, I agree. Everything from system administration to 3D modeling to advanced multilingual academic writing is entirely possible in a context of software freedom and openness. Puffy adds, plus, it is enjoyable to learn new things, like how to contribute to something made by and for a specific set of digital workflow needs by the very people who need to use it. Beastie says, it is settled then. Let us go forth and lead the world out of the cave of software closedness and into the light of software openness. I, Corey, look forward to talking with any or all of you in-person attendees in the hallway after the close of this session. For online listeners, I will check IRC, like I promised, Libera Chat, channel BSDCan 1110. And I'll check there to see if you have posted a question or comment. And I welcome your later questions and comments via email. Now let me open the floor. What questions or comments might you folks have? Please feel free to ask or talk about anything that you might like. Thank you, everyone. Yes, Mr. Dave.
Seems like almost said at the beginning there that Plato predicted the Matrix.
Did I say that? I would have to look into this, Mr. Dave, but I would not be surprised if the folks in the Matrix were not inspired in some way from Plato's allegory of the cave, actually. Or even if they were not consciously aware of that inspiration, right? The story's kind of so embedded into our paths of learning that, I mean, the parallels are right there. Yes?
I heard you describe Plato's writings as the greatest, but not necessarily the best. Was that a potential Aristotelian shade you were throwing?
Oh, so the question is commenting when I made the comment that Plato's writings are the grandest, but I'm not saying greatest, and if that might be Aristotelian shade. No, no, no. I was just simply making the point that in saying that his writings are the grandest and the most elegant and the most well thought out between him and Aristotle, I was just commenting on the quality of the writing as such. And for the record, I'm not saying that either Plato or Aristotle is somehow superior to the other for that reason. But Plato's stuff is a lot more fun to read as something to read. Yes, gentleman in the front.
How do you extend this thinking to things that go beyond your personal device and things that you can control with your hands? It strikes me that a lot of the software that is used these days is increasingly complex and relying on other different services, third parties, et cetera, et cetera. So what you run may not be the full story.
Yes.
Your thoughts.
So the question, excellent question, as all of these have been, is how do we enter into this mode of thought, let's say, at a time in which sort of everything is dependent upon the cloud and interconnected services, and the cloud and interconnected services are often not in alignment with the, let's say, philosophy that I'm advocating here. Yeah, great question. I mean, the first thing that comes to mind for me is in a person's own computing space, somebody really does have a lot of choice about how to operate a system. Now, practically speaking, for example, am I going to host my own email server in 2026, needing to be able to communicate with university email servers, which block basically everything? No, that's a practical impossibility. But I nevertheless can make sure that sort of everything other than the server that I'm using is operating in a way that accords with how I want it to work. So I'd say an approach like that is starting to get to a way of thinking about it. There are kind of practical needs, but a person does have sort of, at least in one's immediate circle, like you said, there's that control, and then looking out beyond that, there are choices people can make. I know some of you folks are actually in contexts in which you are able to host your own mail servers, right? Michael Lucas has a whole new book on that, and that's great. But that's the sort of thing, right, where people have to choose, all right, I do have to just get work done, and things do have to interoperate, but how much can I do to protect the privacy of my intellectual property, and so on.
I have one more.
Yes, please.
Given that a lot of your presentation, I mean, really awesome, by the way, centered around this concept of republic, the res publica, do you think that the public, be the government or be some sort of organization between people, has a responsibility in upholding some of the principles that you're delineating here?
Yes, so the question is, does the public, in the sense of governments, thinking about the fact that the inspiration for this talk is actually an ancient dialogue about governance, what do we think about the application of the principles of the talk for governance? So I would say yes, that responsibility ought to be there. So that's the shortest answer. Done. No, there's a little bit more. Yeah, and we persons who are privileged to live in democracies, republics, right, places where there's ability to vote, to contribute to legislation, and so on. I think that anytime we can vote in favor of at a bare minimum, transparency of what is being used in computing systems that affect the lives of citizens and other persons living in a place, we have an ethical obligation to do so. The path to totalitarianism is lined by apathy towards things like censorship and monitoring. Yes, another question.
So a comment on your last statement. This kind of goes into the ethical source thing. I also think you could probably say that the road to tyranny can be paved by good intention. Ethical source, it's good intention. They want to try to limit access to companies or individuals that they see as problematic or dangerous. But the downside of that is when you start taking chances to allow to use something, that in itself becomes a form of limitation.
Yep, thank you. So the comment is, right, good intentions from something like ethical source ideology. Even among the best intentioned things, the idea is ultimately something kind of tragic can come of that. Was that a fair way of restating what you said? Yeah. Thank you for that comment and observation. I think I'm going to take the cue now to close this session, but I'm certainly going to continue with the hallway chat. Thank you very much, everyone. Have a blessed rest of your day. What shall I do with this microphone?
Anfänger gerichtet, aber welcome to my talk, What Happens If You Write to Def Null? Well, stuff disappears. Thank you very much. Are there any questions? Oh, I'm just kidding. I'm just kidding, of course. I hope you're all here because you want to learn a little bit more about it and what happens behind the scenes. And I guess probably all of you, well, who has written to Def Null before?
Never.
Always everyone? Who has ever seen something that was written to Def Null again? Okay, that's very good. That's how it's supposed to be. I want to hear the story maybe later. So what's the history of this talk? Well, back when I was in university studying, I had the usual operating systems lecture, and we would be talking about how does networking work in general, or file systems, or process management. And after the lecture, I would always take my laptop, go to some quiet corner, and then, look into the source directory and see how it really works behind the scenes. And I always found this quite interesting and fascinating, and I hope I can share some of this fascination with you and maybe also give you some good starting points when you actually want to do your own explorations into the kernel space. So this is our kind of example command today, and of course this is quite a useless command. We're just reading in a file to then write it to def null. But it kind of serves its purpose well to kind of give us some direction on where to go. And well, this is our go-to example, and we are looking at OpenBSD. So, and I also try to provide the references to the source code so that you can also get some intuition how is the code organized and where would I have to look for something. And if you approach this problem with no prior knowledge, you might assume, well, this redirection to def null, this is just some feature of cat. When cat sees that as part of its arguments, it just prints it to nowhere or it ignores the output. But that's not the case. Cat actually doesn't see this redirection part at all. For cat, it's business as usual. It just reads the files and then prints them to writes them to standard output. And there's a little star here, which means we have to clear a little bit something up, but we'll do that later when we know more about what's going on. And the source for cat is in bin cat. Actually, this redirection is part of a shell feature. And what this means is that the output of the command is redirected to a file. And for the shell, def null is just some file. It could be anything else. It just says, OK, I have to run a command, and I have to write the output to this file, nothing more. And you find the shell source code in the same directory as the cron shell source code. So before we can write to def null, we first have to open def null. So how do we open a file? Most of you are probably familiar with the library functions like fopen or file read or whatever your programming language provides. And what they all have in common is that behind the scenes, they will be calling a system call either open or openadd. And system calls are the way how programs usually interact with the kernel, or if they need the kernel to do something. If you want to write to a file, open a network socket, create a new process, get some memory the process can use. That's always system calls. And how that works is that there's a CPU instruction which then switches from user mode to kernel mode, and then CPU jumps to the kernel part which then handles the system call. And of course, there's not a CPU instruction for each and every system call. There's just one instruction. And then part of the arguments is then which system call does the program actually want to use. And this is the system call number. And once we do that, we land in kernel space. So we are now in the kernel. Welcome. And when we are kind of in the kernel, we are using a blue background. And the kernel source code is in the sys directory. So what kinds of directories can we find in sys? Well, we first have the kernel directory with like the kernel functions. We have the net directory, which contains the source code of PF and also virtual network devices. We have the dev directory, which contains the drivers for physical devices. We have NetEnet directory, or 6 for the IP protocol, TCP, UDP. We have the Arch directory for architecture-specific parts of code that are, specific to one CPU architecture. And of course, there are many more, but this is, I think, a good starting point to kind of know what's going on. I now introduce a few little parts just to, if you explore the kernel, to help you get started, to kind of maybe already know the words a little bit, because often there are abbreviations used, and they're never explained, or very seldomly, and then it helps if you know what the abbreviation stands for. For example, there is the kernel log, and the kernel log is like the most coarse log there is. And so it's like one instance, and then it's used like for the big operations where everything else has to be logged out. We have copy in and copy out. This is used to copy memory from user space to kernel space. So for example, in our open call, we provide a buffer with a string, and this buffer is copied to kernel space so that while the kernel is operating on that, user space can change things around and do other silly things. There is a split for some functions between MI and MD parts. MI stands for machine independent, and MD stands for machine dependent. So the general code would operate with machine independent parts, which then call the machine dependent parts, which depend on the CPU architecture and such. And softc, I didn't know for a long time what this stands for. This stands for software context. So if you have some device driver and the kernel needs to maintain some state, it does so in the software context. And it's just helpful to know what this stands for. And another acronym you might hear somewhere is KNF. This stands for kernel normal form. This is like the style the kernel source code uses and how it is formatted. So how does the kernel handle the system call? Well, first it does various security checks, so pledge, pin syscalls, and then it looks up based on the system call number, okay, which function do I actually need to call inside the kernel code? And this is, the system calls are listed in syscalls.master. And this is an excerpt how this looks like. On the left, you can see the system call numbers. Here are options for the system calls. STD means that the system call is always included. So there are also some system calls that are only present in some configurations. No log means that the kernel does not have to acquire the kernel log before calling this function. In the beginning, every system call required the kernel log, and over time this has been reduced. This does not mean that they never need the kernel log, but they don't need it at first. And on the right, you can see then the function signature of the function that is called. So if you're now tasked with finding a system call, what's very useful is a system call starts with sys underscore, and because of the kernel KNF, you can just easily use this grab pattern to grab for a system call. If you want, for example, to find the source code for an open system call, you just search for any line that starts with sys open, and then you'll find it. Before we now continue what our open system call does, we have to quickly talk about file systems. So file systems are backed by block devices. This will be important later. They contain different types of objects. Files, directories, block devices, character devices, symlinks, etc. And in FFS, the fast file system, which is the default on OpenBSD, these objects correspond to inodes in the internal part. Now, we know how to find sysopen. And sysopen is in the VFS syscalls file. And what it does, it turns a path, the one we give it, into a vnode. So the question is, what is a vnode? And for that, we have to know that there is something called the virtual file system layer. And most kernel routines only work with this virtual file system layer. And the idea is that this keeps the kernel logic independent of the actual file system that is used. Also, there are, of course, can be multiple file systems in use and mounted onto each other. And this keeps it all generic. So if you come from an object-oriented language, just think about it as kind of an interface, which then different file systems implement. And these file systems then implement operations. Like, for example, if you want to mount a file system, if you want to unmount one, if you want to get a root node of a file system, etc. And you find that in the mount.h. This is not a typo. So it's actually sys for the kernel source code, and sys again are where the include files for the kernel are, and then mount.h. So with that out of the way, what is a vnode? You can probably already guess. It's what the kernel uses to represent a file system object. And what's an interesting tidbit here is that once a certain piece of memory is used as a vnode, as long as the system is running, it will never be anything else than a vnode. And the reason is that there is a lot of caching going on, and these keep weak references to the vnodes, so you kind of never know what else might have a reference to this vnode. So you have to just make sure that it matches the layout of a vnode forever. And there is a field inside that vnode which says which ID it is, which then, when the vnode changes, the ID changes as well. So the cache then caches the pointer and this ID, and then it looks like, oh, well, yes, is this still the same vnode which I originally cached? If yes, I can return it. If not, I'll have to, it's a cache miss and have to do the work again. And you find that in the vnode.h, the definitions. So interfaces in C, how does that work? You may have seen some form of this before in some other libraries or code. What it boils down to is that you have some function pointers and void pointers. And the function pointers are like the interface methods. And they then use the void pointer to store the implementation object they need. So for example, our vnode has a structure called vops. And this vops structure contains like all the vnode operations like reading, writing, syncing, and also has a field for a data pointer, which then, depending on the file system, is filled with whether the file system then needs to execute the operations. And when the vnode is created, whatever creates the vnode also makes sure that the vops structure is set correctly to the correct functions. And yeah, some examples for what these virtual operations, vnode operations contain: write, read, or getting attributes. And just that if you're looking around, there's also something called struct VFS ops. These two are not the same. The latter one is used for the generic VFS operations I've shown earlier, like mount and unmount, and vops is used for the operations on vnode. So now, armed with all that knowledge, we can then turn this path into a vnode. And there are two functions mainly responsible for that. That's namei and VFS lookup. And how they work in this case is they start at the root node and then go piece by piece, looking up in the directories the next part and going through that like this. And while they're doing that, they have to do certain things. They have to check for permissions, right? Is whatever process trying to open that file even allowed to see that? They have to check like for symlinks and follow them, but also making sure that you don't end up in a loop. That would be really bad. And in total, these two functions are over 600 lines of code, so there's a lot of going on, just turning a path and finding the corresponding vnode. and the code is in VFS lookup. Now I mentioned here we start at the root node. And the question is, okay, well, going from one component to the next is quite obvious how that works, but how do I know where to start? Where does this root node come from? So well, there's a global variable called root node, and that's just where the root node is stored. But you can see there is no initializer. So you can guess from that that this has to be initialized quite early. And now where would that happen? Well, I'm not sure if you know, but this is also one of the things I find super cool. The kernel has a main function, just like any other C program. So the main function then just sets the root node during the startup procedure. And if you are interested in how does main look like for a kernel, you find it in init main. So we now have a vnode, and these vnode operations we do on them are then translated, because we're using FFS, to the corresponding FFS operations. And what FFS then does, it reads the corresponding inode from the block device, from the disk. And again, here's a little star. We will talk a little bit more about that later. And now the question is, okay, we are getting back an inode, but we haven't, what are we expecting? What makes DevNull special in the first place? And to get a bit of hint of that, we can look at it in the, with the ls output. So if we look at it, we see something like this. And to kind of compare it, we just now also do the same for a regular file. And we can see two differences. The first is DevNull has a C up there, and the regular file doesn't. And also where the regular file has a file size, DevNull has 2,2, whatever that stands for. So C means DevNull is a character device, and 2,2 are the major and minor numbers. And what's the purpose of the major and minor numbers, we'll see later. So FFS will find a character device inode, and once it gets that, it creates a new vnode with that. And because the vnode is, the inode is special, it's a character device, it doesn't use like the usual vnode operations for writing and reading. It uses like special vnode operations. So it's a different structure than for a normal file. And then once it's done, it takes that vnode and returns it to whoever asked. Now, we have this vnode, but you probably have never seen a vnode when programming. And it's because we can't really just return that to user space, and it probably would also not be a very good idea to just return that. So what happens is that the vnode gets wrapped in a file structure. And struct file is again one of those interface structs, which is used for file-like things. For example, it's also used for sockets or pipes. And each process has a structure called file desk. And in there, there's an array. And this new file is then just placed as a free spot in this array. And the index of where this file structure is placed becomes then the file descriptor. So probably, who has heard of file descriptors before? So if you ever wondered where this number comes from or what this means, it's just the index into this array where you can find a corresponding file structure, which then contains the vnode, and which then again contains something else. And there are some conventions around file descriptors. File descriptor 0 is used for equivalent to standard input, 1 is standard output, and 2 standard error. And it's important to know that this association is just a file descriptor. It's just a number. So if you close standard error and something else gets opened in position 2, it will be just treated by other libraries again as standard error, and they will write to it. And this can be a problem, for example, if file descriptor 2 is your database, and suddenly some library prints to your database, and this is one of the ways how you can corrupt, for example, a SQLite database. So you can just Google that. There's like a list on how to do that. And this is one of the options how we can corrupt a database by simply opening it up for a file descriptor where other parts of the program write to. So we have our file descriptor. And now we can use that to actually write to def null, which we wanted to do from the very beginning. So we use the write system call, and we give it the file descriptor we want to write to as an argument. And then we again go to the kernel. The function we're going to look for is syswrite. And the first thing it does, it takes again the file descriptor, goes to the associated file descriptor structure of the process, and looks up, okay, which struct file does this correspond to? And then it says, okay, calls the generic fowrite function. And this then gets calls or gets translated to the vnode write operation because it's a vnode inside. And this, you remember, the vnode operations were the special operations. And this means it ends up with the special write function. So this is how special write looks like. And it switches on the type of vnode. And for a character device vnode, it then does index the cdef sv array. And you can see it gets indexed by the major number of the vnode. And before we have seen the major minor number of def null, which is 2 and 2. And this is what the major number is used for as an index into this character device array. This array is actually architecture specific. So for each architecture, there is a definition of this array. And what's in these slots in this array is, again, just a structure with, again, file pointers. And major number 2 are the special memory special files, def null, def 0, def mem, and def kmem. And well, here you have now to replace x with whatever architecture you prefer, because there is like a conf.c for each architecture. And now you can see, okay, well, the first part we index into this array, and then of this structure we call dwrite, which is then a function pointer which points to whatever this memory special file wants to use to writing. So with that, we end up in this function to write to memory special files. And for that, we now use the minor number to find out, okay, which memory special file we want to use. So the major number is what kind of character device. And the second one is then, okay, which of these actually do we want to use? And here we have case number 2. We check that we actually want to write. And what we do is we simply set, okay, the remaining bytes to 0. So this SID is used to kind of keep track of, okay, how many bytes do we still need to write? And what def null simply says is, no bytes remaining, everything is written. And with that, we have successfully found the end of the journey for whatever we're writing to def null. And of course, what's remaining is that we return the bytes that were written back to user space as the result of our system call. Now, we still have a few things to clear up. So how does that actually work, that the shell is redirecting the output of cat to def null? It's not that and what you might think is, okay, well, the shell just reads the output of cat and then writes it to def null, but that would be somewhat inefficient. And what you can actually do is you can pass file descriptors to other processes. So what the shell does, it opens def null, takes the file descriptor, and then when it launches cat, it simply replaces file descriptor 1 of cat with the file descriptor of def null. So for cat, it's business as usual. It simply writes to file descriptor number 1, which now refers to def null and goes the entire route you've just seen. And normally, now, if there would be no redirection, usually what is used as file descriptor 0, 1, and 2 is the file descriptor of the terminal, which then leads for the content to end up on the terminal. I also said that cat does know nothing about the redirection. And in this case, this might be true, but there are ways for applications to kind of inspect file descriptors and kind of figure out, are they pointing to a TTY, or maybe it's a network socket I'm dealing with. And one example here is for LS. Maybe you have noticed when you just use normally LS, you get like this tabular layout with columns. But if you use it in part of a command pipeline, you get them one by one, like each entry on its own line. And this is how LS knows whether it's part of a command pipeline or not, because if it's part of a command pipeline, the file descriptor 1 is no longer a TTY, it's something else. What we also were missing is, how do we actually read an inode? And I mentioned it before, the file system is placed on a block device. And the block device is, again, a special device. And there's, again, a vnode for that. So what FFS does, it uses, again, the generic vnode operations to then read from the block device. And this ends up in a very similar place as before. Instead of the cdef SW, it ends up with bdef SW. And this is like the array of block devices that are present on systems. And again, the major number kind of refers to the type of device, for example, SCSI. And then the minor number is, again, used, okay, which of these SCSI devices does this refer to? So you can see it uses the same interfaces over and over again, all the way down. And bdef SW then makes sure that this ends up on the in the right physical device driver, which then does whatever it needs to ensure that it ends up on the disk or not, or coming from the disk. Now you might wonder, okay, but where do all these devices actually come from? And the answer is there's a command, mknot, which can be used to create these special files, well, character and block devices, and where you have to kind of say, okay, which major number and which minor number do you want? And you kind of need to know, okay, which major and minor numbers lead to what. And there is a makedef script, which is used to, during the installation, for example, to populate the dev directory with all the correct inodes. And this is a difference from other operating systems, because on OpenBSD, these are still inodes that are present on disk. And most like Linux and FreeBSD use synthetic file systems, where the file system part is handled in the kernel and there are no calls to disk. Maybe some general tips if you go exploring the kernel, or like want to learn more, or learn what is a command doing. There are two commands called ktrace and kdump. And they're really useful because what happens is, if you run a command with ktrace, it produces a ktrace.out. And you can then use kdump to print this file, and this file contains like all the system calls that were being made by the process and what they returned. So if you ever wondered, okay, what is this program doing under the hood, you can just use that to kind of inspect what system call it does. This is also super useful if you want to find out where a program is keeping its configuration files. You just ktrace it and then look for the open calls, and then you know where the files are hidden. Also, check out the man pages. Section 9 of the man pages is used for kernel documentation. So you can, for example, just look up the documentation for the name I function. Now, what we didn't see in this exploration is, for example, all the caching that is involved in making things go fast. Of course, not every time something is right from this. Ideally, it's cached at all the layers and returns much quicker. You also haven't seen much of the security that is involved, because after all, you have to validate all the information you get from user space, make sure that they're somewhat sane, and perform various checks. And what we also only have seen very little is all the locking that is involved to making sure that if multiple processes running in parallel, that the system calls don't interfere with each other and that the kernel stays properly locked and fields are accessed in the correct manner. So, in conclusion, getting rid of stuff is surprisingly complex. And I hope I have provided you now with a good starting point to do your own explorations and satisfy your own curiosities when you want to find out how something works in the kernel. And so, have fun in your adventures.
Yeah, if I remember correctly, at one point you mentioned that the major minor numbers are CPU architecture specific. Does that mean that the different CPU architectures allow different types of facilities that allow you to actually write to DevNo?
The question is about the major minor numbers and if they're CPU specific. In this case, it's the same for all architectures because they're like special memory files. But for other character devices like terminals or like physical block devices, of course the numbers differ a little bit, and that's where the general mechanism comes from. But for this case, I think it's always 2-2.
Would I be correct in understanding that basically the kernel goes, yep, you're good as far as writing goes, and so that would bubble all the way back up to the user space application, and then the user space would just basically free that memory as it needed to, or the process would die and the memory would be cleaned up? Like if I cat file, pipe it to devnull, devnull is going to say I'm good right away. Where does the memory actually get free? Is it just relying on the application to be free?
Which memory?
Well, so the contents of my file are being sent this direction.
Okay.
Presumably that's being written, and so it would be up to the application to simply say I'm done.
The question is about the memory that is being the contents of the file being read. When and where are they freed? Well, the application, if it usually reads them into memory and then calls the write system call with that, and independent of what's going on, the kernel copies that in, and then afterwards, when it finishes write call, frees that, and then the application is again responsible for its own memory and making sure that it gets cleaned up or overwritten with the next batch of bytes to read.
Perfect. Thanks.
In that case, thank you very much. And I mean, if you have other questions, you can come up later or have fun exploring the kernel.
All right, let me get the other one. Wait, can you, there we go. All right, test, test, test.
All right, you're good.
Thank you.
Okay. Thank you for coming. Today I'll talk about universal place storage on FreeBSD, focusing on the UFS host controller driver added for FreeBSD 15.0. I will first explain what UFS is, why FreeBSD needed a UFS driver, and how the UFS driver fit into the FreeBSD storage stack. I'm Jae-yoon Choi. I work as a system software engineer in memory business at Samsung Electronics. I'm in the SSD software team working on open source and OS related storage project. I'm the UFS driver owner on Google Fuchsia OS, and I'm also a FreeBSD committer. In FreeBSD, I maintain the UFS driver, which is the topic of this talk. I also wrote about this work in FreeBSD journal article. Today I focus more on the driver internal and implementation decision behind it. Universal Place Storage, or UFS, is high-performance embedded flash storage standard designed to replace eMMC in smartphones and embedded devices. As shown in the photo, a real UFS product is very small BGA package, but inside that package, there is not just a low NAND flash. It also contains a NAND controller and firmware. In that sense, it works like a small SSD in a single package. UFS targets mobile and embedded systems. So it has satisfied three requirements at the same time: high bandwidth and small package size and low power. Unlike PC or server SSDs that primarily chase peak performance, UFS designed for devices where battery life and package size matter. For reference, in this talk, UFS means Universal Flash Storage, not Unix file system. The name overlaps, so I want to make that clear at the beginning. That is why FreeBSD UFS driver is named after UFS HCI. To see why UFS matters, it helps to look at storage interface evolution. Enterprise and server storage moved from SCSI to SAS to NVMe. Client PC storage moved from IDE to SATA to NVMe. Mobile and embedded storage moved from low NAND to eMMC to UFS. New storage interface does not appear very often. Just as NVMe became the main high-performance storage interface in server and PCs, UFS is becoming the next generation mobile storage interface after eMMC. Our system is split into two main parts: the host controller and the device. The host controller is integrated into the application processor SoC. The UFS driver controls this host controller. On the other side, there is a UFS device in a BGA package. And inside the package, there is a NAND flash and a device controller. The host and device are connected by an MPI link. UFS does not use a parallel bus like eMMC. It uses a high-speed serial link based on MPI. As the diagram shows, the driver does not directly control NAND. It talks to the device controller through the host controller. And the actual data is stored in NAND flash inside the UFS package. So a UFS driver is not low NAND flash driver. It controls the UFS host controller and communicates with the UFS device through that controller. This table compares eMMC, UFS, and NVMe. The main message is simple. Compared with eMMC, UFS has much higher bandwidth. Compared with the NVMe, UFS is not trying to win peak performance. It is designed for mobile and embedded and automotive system where package size and power matter together with performance. UFS is not just fast flash storage. It also several features designed for mobile workloads. On the performance side, features such as write booster and MCQ helps burst write and high Q depth I/O. On the power side, features such as auto hibernation and deep sleep and high speed gear reduce idle power and adjust link power dynamically. The link does not have to stay at maximum speed at all time. Because of these characteristics, UFS is not just a slower NVMe alternative. It's designed around the performance and power balance needed by mobile systems. For example, in tablet, replacing NVMe with UFS increases battery life by about 30 to 90 minutes. UFS is defined by separate specification for the device protocol and for the host controller interface. The driver needs to understand both sides. As the UFS specification evolves, link bandwidth keep increasing. Each major version also adds features for mobile storage workload. The point is that UFS is still actively evolving. FreeBSD support is not just about one device generation. The driver has to keep up with a standard going forward. Now let us look at why FreeBSD needed a UFS driver. Historically, FreeBSD has been used heavily in server environment. In those systems, the common storage devices were NVMe, SATA, and SAS. So UFS was not high priority driver for a long time. But recently, projects such as FreeBSD laptop project have pushed FreeBSD toward the laptop and mobile class device. In those systems, UFS cannot be a storage option. It is already default storage choice in many flagship smartphones and expanding into embedded automotive and laptop systems. Intel's 2026 low-power Wildcat Lake processor also include a UFS storage option. So UFS is no longer only smartphone storage. It is moving into the kind of a low-power laptop that FreeBSD want to support better. On-device AI is another reason storage bandwidth matter. Loading large language model directly on the device can require more bandwidth than eMMC can provide. In that case, UFS become more natural storage choice. Other major operating system already has UFS support, but FreeBSD did not. So the question that started this project was simple. Why doesn't FreeBSD have a UFS driver? The project began in July 2024 with proposal on the FreeBSD hackers mailing list. Actual work started in January 2025 with analysis and design because I was new to FreeBSD. So I first had to understand existing storage stack before writing driver code. During the first 2 months, I studied CAM, the SCSI path, and the existing NVMe driver structure. The goal was to make a new UFS driver that naturally fit into existing FreeBSD storage stack. In March, I started driver implementation and spent about 2 months building the initial driver. QEMU prototyping helps keep that implementation loop fast. In May, I requested early code review. That decision mattered. If a logic driver stays private for too long and get reviewed only at the end, changing direction can be expensive. Fortunately, reviewer accepted the overall direction. with analyze first implementation nest and early review, the driver was developed and merged in about 6 months. I especially want to thank Warner Roche, Yuan Hu, and Ed Mast, and other previous reviewers who helped shape and driver during review. Okay. Now let us move into UFS architecture. I'll start with the system view and then show the protocol layer view. This diagram shows the whole UFS systems. On the left side, inside the application processor, there is a UFS host controller. On the right side, inside the UFS target device, there are device controller and NAND flash. The important point is that the driver does not control NAND directly. A storage request starts in CAM, passes through the UFS driver and the host controller, and reaches the device controller. The device controller then handles the UFS request and platforms the actual NAND read or write through the flash translation layer. So the role of UFS driver is not control NAND. Its role is to take cache command from CAM, build UFS request, and submit those requests to the host controller. The UFS system model can also be viewed as a protocol stack. From this view, the main layer are UIC, UTP, and UAP. UIC is the UFS interconnect layer. It creates and maintains the MPI and UniPro link. In simple terms, it is responsible for the link that let the host and device communicate. UTP is the UFS transport protocol layer. It carries requests using UPIU packets. UAP is the UFS application layer. It is the cache-based command layer used for read, write, inquiry, and task management. This is why UFS fit naturally into previous storage stack. The device manager on the left side handles control path operations such as query, power, and configuration. Now we move to the driver design. The key point is simple. The UFS driver does not create a separate storage stack. It attaches to the existing BSDCan subsystem as a CAM SIM. From the top, Geom is the generic storage transformation layer for disks, partitions, and block device. The CAM peripheral, such as DA, creates the disk view and builds cache command. CAM passes each request as a CCB, or CAM control block. This is a request object that UFS driver receives from CAM. CAM XPT routes those CCBs to the right SIM. CAM SIM is the host controller driver boundary. The UFS driver implements that CAM SIM, receives CCBs, wraps cache command into command UPIU, submit them to the UFS host controller, and returns completion to CAM. So our previous storage stack can treat UFS like a normal cache stack. The initialization sequence proceeds from the hardware side upward. If a lower layer is not ready, the UFS layer cannot start. First, driver enables the host controller and perform UIC link startup, which bring up the MPI and UniPro link. Link startup is the first milestone where the host and device become able to exchange packets. Before the link is up, driver cannot send any request. So this must happen early. Next, driver prepares a UTP request path. Once request descriptor and the command path are usable, it sends a NOP UPIU. NOP UPIU is the first round trip that checks whether the host and device can exchange UTP request and response before I/O request. During bring up, this is very important milestone. After that, driver queries available lanes and maximum high-speed gear, then switches the link to the selected high-speed mode for the maximum bandwidth. Finally, after CAN bus registration, previously can scan the UFS device and attach it as a SCSI disk. Once all of this is done, we can see the UFS device as a disk. And the driver is ready to handle real I/O requests. The next chapter shows how those I/O requests move through the driver. I/O path. I will walk through how a single SCSI I/O command comes down to the CAN and return as a completion. When a CAN CCB arrives, the UFS driver creates a UFS request from it. At a high level, the request goes through 4 stages: command, data, submit, and completion. The next slide walks through these storage one by one. The first stage is command path. A CAN CCB contains a SCSI command. The UFS driver wraps that SCSI command in command UPIU. UPIU means UFS Protocol Information Unit. It is the request and response format used between the UFS host controller and the device. The controller, the command UPIU also carries UFS transport metadata such as LUN, data direction, and expected transport length. The second stage is data path. The command UPIU describes the request, but it does not contain payload data. The PRDT tells the host controller where the data buffer is in memory. PRDT means physical region descriptor table. When the driver split an I/O buffer into physical segment, each segment becomes a PRDT entry with DMA address and length. The UFS host controller follows these entries to perform the DMA transfer. At this point, the driver has to prepare the command UPIU and PRDT, but it still needs to track request context until completion. For that, I used the proven FreeBSD NVMe driver style request tracker. The tracker keeps request state, DMA mapping, timeout, slow state, and completion context together. This keeps the request path simple and easy to review and ready for MCQ-style queue expansion. In current SDB single doorbell path, the driver assigned a tracker to request slot before ringing the doorbell. The third stage is submission path. To issue multiple commands concurrently, the driver picks an empty SDB slot and assigns a tracker to that slot. The SDB path uses multiple request slots and one doorbell bitmap. SDB means single doorbell. Each bit in that bitmap tells the UFS host controller which slot is ready. The driver then fills the slot with prepared request. The slot number is key index. It identifies the request slot, the tracker metadata, and the doorbell bit. After the slot is ready, the driver sets the doorbell bit. The host controller fetches the prepared slot by DMA and sends the request to the UFS device. The fourth stage is the completion path. When the UFS device finishes I/O, it returns a response UPIU. The UFS host controller updates the completion state for that slot, clears doorbell bit, and write completion interrupt. The driver used the throw number to find the tracker metadata and recover the original request context. This is reverse lookup of the submit path. Slot n point to tracker n. Then the driver checks response, UPIU, status, and scarce sense data. It cleans up DME buffer and throw state and returns the CCB to CAM. At that moment, the upper storage text is that the IO has completed. The second design decision is the submission backend. The IO path I have shown so far is based on single doorbell, which used a throw-based request list. But UFS 4.0 adds MCQ, or multi-circular queue. SDB and MCQ use different submission structure and registers. If the common IO path had to know those different directly, the driver would become more complicated. So the driver hides the backend behind the QOps function pointer table. The current driver uses the SD backend through this table, and same boundary can also cover on future MCQ backend. The common IO path only calls that QOps table. It does not need to know whether backend is using SDB or MCQ. This keeps request tracking and DME handling simple while isolating Q backend choice. Validation used two stages. Most functionality was developed and tested quickly in QEMU, and real hardware was used to confirm actual controller and device compatibility. The main development environment was the QEMU UFS emulation. This feature was contributed to QEMU in 2023 by my colleague Jae Kim at Samsung. It let me repeat tests quickly without waiting on hardware for every change. Then I used real hardware to confirm compatibility with real controllers and devices. The test platform were Intel Lakefield and Alder Lake systems on x86 and a Qualcomm Snapdragon X Elite system on ARM. The current driver supports PCI and ACPI attachment paths for UFS host controller. For performance validation, I compared the FreeBSD UFS driver with the Linux UFS driver on the same hardware. Sequential read and write are almost the same between FreeBSD and Linux. This means the basic data paths and DMA paths are working properly. And there is no large bottleneck in sequential workload. But random high queue depth remains the main optimization area for single doorbell paths. But the important result is that the initial FreeBSD UFS driver already performs close to mature Linux UFS driver. Now I show you a short demo of the UFS driver on FreeBSD. For this demo, I used QEMU UFS emulation instead of real hardware. So first, I create a 1 GB raw disk image for the emulated UFS driver. Okay. Here is block. Then I start a FreeBSD VM with QEMU UFS emulation. This is a device UFS creates an emulated UFS host controller. Okay. Now the FreeBSD VM is booting. During boot, the emulated UFS controller should be detected, and the UFS HCI driver should attach it to it. After boot finishes, I'll check the depth from the kernel log. Okay. First, I check UFS HCI module is enabled in bootloader config. Okay. In the prepared demo image, UFS load yes is already there, so I can go straight for the check. First, I check the kernel log. Okay. This is already patched next.
No, I'm talking the last 2 lines are my fault.
Oh yeah. Yeah, we know that. So here we can see the UFS HCI 0 is attached, and UFS logical unit is posted as a DA0. Now I run the PCI config. Okay. This confirms the previously detected the QEMU UFS host controller. Yeah, QEMU UFS host controller. And then I checked CAM list. Okay, here disk appears as a D0, and under UFS HCI 0, yeah, UFS 0. Next, I checked disk information. This shows 1 gigabyte disk, attached through the UFS HCI 0. So now we have confirmed 3 things. The PCI UFS controller is detected, and CAM disk is created, and the disk is attached through the UFS HCI 0. Finally, I run simple write and read tests with the FIO. This is write workload. Okay. We can see the bandwidth is 296, and then I run the read workload. This is read workload. Yes, this. Oh. Yeah, we can see the 346 megabyte per sec. But this is QEMU emulation, so exact bandwidth is not pointed here. The point is that I/O works correctly through the previous UFS driver. So in this demo, previous detect the emulated UFS controller, attaches UFS driver, create DA0, and run simple I/O on it. Okay. Next, let us look at future work. The next step are as follows. First, performance. The next performance work is to improve random high queue depth I/O and add MCQ support for multi-queue scaling. The QOps structure described earlier was designed with this extension in mind. Second, power and recovery. hibernation, suspend resume, and error recovery need to be strengthened because UFS is mobile storage. Power management is important for real usability. Third, platform support. The current driver support PCI and HCPI attachment path, but ARM device tree-based platform still need support. Fourth, spec tracking. As UFS 4.0 and 5.0 adds new feature and higher bandwidth, the pre-BSD driver needs to follow those changes. Finally, community feedback. If you have a UFS use case or requirement, please tell me. I will try to incorporate them into future work. Finally, here is conclusion. The UFS driver supports UFS host controllers through the existing BSDCan server system. The implementation keeps the I/O path simple and extensible by using request tracking inspired by FreeBSD NVMe driver and QOps for Q backend abstraction. UFS is expanding across mobile, embedded, and laptop system. FreeBSD now has a practical foundation for supporting this UFS-based hardware. The question that I started this project was, why doesn't FreeBSD have a UFS driver? The answer is now it does. Thank you for listening. Do you have any questions? English is not my first language, so please speak a little slowly. Oh, okay.
I've noticed on your test sure it's part of QEMU errors about cache flush support.
Yeah.
How well actual devices support actual SCSI commands? Because cache management can be critical for ZFS, for example.
You asked why UFS didn't support cache?
Do actual devices support cache flush?
Because UFS device doesn't have a cache, because it doesn't have a DRAM inside the device. It doesn't have a DRAM.
But they still need to update translation table or anything, or it's like everything written immediately persistent, you're saying?
Yeah, sorry?
Every write immediately persistent. There's nothing to flush for make it survive.
Yeah. We don't need a flush. Just if you write to the UFS, it is written because you don't have a cache and.
So in case of power loss, it will recover everything inside.
Yeah. So maybe we have a very strong recovery logic in the UFS device. Yeah.
Normally SSDs have either some capacitors or.
Yeah. Normally SSD has a capacity, but it doesn't. Yeah. I think in mobile device like smartphone, the application is guaranteed to the right. Yeah, so it's a little different from server application. Yeah. Any other question? Yeah, if you have additional questions, please send me an email. Thank you for listening.